Uh, yeah, so I think Matthias, he gave a very good introduction of all the PVT experiments and the most important things that we need to remember, like what we get out of those experiments. And now we will go into a bit more details of how the experiments are done, what are the measurements done on the PVT experiments, how the data is reported, what are kind of the uncertainty limits on the different measurements. And we start with this slide, which is a very good slide, giving an overall picture of what experiments are done on what kind of fluid. So first is about the sampling. So bottom hole samples. Uh, so you can collect bottom hole samples for the oil samples, and for the gas condensate, it's usually not recommended to do the bottom hole sampling for the reasons we have discussed already. The recombined samples or the separator samples, they are recommended for both oils or gas condensate or any other fluid type. We have the CCE or CME experiments. These are generally done for all types of fluids, whether oil or gas condensate. And that's generally the first experiment you do because you need to know what kind of saturation pressure. Because other experiments like DLE or CVD tests, those tests generally start from the saturation pressure. The DLE test done for the oils and generally for volatile oils or near critical fluids and gas condensates, we generally recommend doing CVD instead of the DLE experiment. Separator test then it can be done for both oils and gas condensates. It's like you and if like this experiment, if this is done for a gas condensate, then usually the gas condensates have to be very rich or near critical gas condensates, so they end up giving you more separator oil, because like if it's a very lean gas condensate and if you do a multi-state separator test in the PVT lab, then you get very small volumes of the separator oil, and which are very hard to measure accurately.
Question?
Yeah.
Yeah, may I ask you, could you please explain why differential liberation test is not recommended for gas condensates?
Yeah. So that's a very good question. Yeah, so the question is that why the DLE experiment is not recommended for gas condensates. And like the first reason, I guess there are multiple reasons, and the first reason is that the DL, if you compare the DLE experiment versus a CVD experiment, CVD experiment replicates the performance of the gas condensate reservoir almost exactly compared to the DLE experiment. Because what happens in the, we will see how the CVD experiment is conducted, and in the CVD experiment, uh, you deplete the gas condensate reservoir, you get this equilibrium oil, which is your liquid dropout, and then you continue producing the equilibrium gas, which it represents very closely your well stream composition that you are expected to produce with the depletion of the field. So this CVD experiment, this is generally a very close representation of the depletion performance of your gas condensate reservoir. Whereas DLE experiment, the way it is done, so you generally have you start with a total composition, uh, and generally since it is done oil, so you have a total composition of oil. But if you do it for the gas condensate, then you will have only the gas phase, and then you deplete it and you get the equilibrium oil, and then you remove the entire gas out of the PVT cell. And that's not how generally the gas condensate reservoirs are produced. Yeah, even the oil reservoirs are not produced like this. So generally, the DLE experiment is not recommended because it's you are not replicating the reservoir depletion performance of the reservoir. Certainly not for the gas condensate reservoirs. And another reason why the DLE experiment is kind of dangerous experiment for the gas condensates is because you have a very rapid change in the total composition in the PVT cell. So you start if you start the experiment at the saturation pressure, which will be the dew point, you will have only the single phase gas in the PVT cell, and then when you will deplete it, you will get below the dew point, you will get an oil phase and a gas phase, and then if you remove the entire gas phase, now the total composition in your PVT cell becomes an oil. So you get a very drastic change in the total composition from the gas phase being to the oil phase. And if there is any measurement errors, then in getting the right total composition in the PVT cell in the lab, you will screw up the entire PVT experiment. So yeah, so that being the total composition being correct at the first depletion state, it's very important for the DLE experiment to be conducted accurately.
It's also somewhat similar to what Matthias is talking about, the compositional path of the reservoir.
Yeah.
Is that the DLE doesn't come close to following the compositional path of the producing reservoir.
Yeah.
The CVD doesn't either, right?
Yeah.
It doesn't follow the same path, but it's closer.
Yeah, but for the gas condensate, yeah, it's very close.
Yeah.
Yeah.
But even there, it's not the exact. It's just closer.
Does this answer your question?
Yes, thank you.
Very good. Another question here. Yeah. It's the same. Okay. Yeah. So I think So very good question here. So we have the multi-state separator experiment, and yeah. So you can also do the multi-state separator test for both oils and gas condensates, but you have to be careful that the gas condensates have to be rich enough that it gives you enough separator oil volumes that you can measure accurately in the PVT lab. And then CVD again, it's recommended for the gas condensates, but it can also be performed for the oils. So you can see the different symbols. What do they mean here? Can be performed for the oils, and generally for volatile oils and near critical fluids, we generally recommend doing CVD instead of the DLE. And the C7 plus GC simulated distillation, that's like the compositions we generally get from the gas chromatography. So this guy here, and that's done for both oils and gas condensate, of course. The TBP distillation, it can be performed for both the oil and gas condensates, and that's usually very good PVT measurement for EOS model characterization. And then you have this swelling test, multi-contact experiments, the slim tube experiments. These can be done for both oil and gas condensate, depending on like whether you are planning to do gas injection or not. Yes, there is another question. Yeah.
Yeah, sorry, I just wanted to ask you one specific question. For example, if we need for gas condensate field, if we need composition at particular date, for example, in the future.
Yeah.
So if we use, for example, PVTI,
yeah.
And which is the best experiment for that prediction, for example, at composition at particular date inside the well, for example, if we need something related to some restriction with the in bottom hole.
So you mean to use the PVTI to predict the composition, the future composition of the gas condensate well?
Exactly, yes.
Yeah. So the first requirement is that you need an equation of state model. I believe you may have it. And then the second requirement, you need a composition, like an in situ representative composition with an equation of state model, and you just simulate the CVD experiment with this PVTI software, and you should know like what average pressure, like in future, at what average pressure average reservoir pressure you want to estimate the composition.
But
so,
it does. Sorry for disturbing, but it doesn't matter if we need the composition inside the well, in the bottom hole, or in the reservoir, for example.
Yeah.
Because in the well, because of segregation, the gas comes to the top of the well, right? And we have maybe, I mean that if there is any possibility to use differential liberation experiment in this case.
To create the black hole dip?
No, yeah, you mean like you want to, Curtis?
I think he's not there now.
He's trying.
Yeah, hi. I just joined, but I didn't hear the question.
Can you repeat the question to Curtis?
Yes. For example, we have a gas field, and we want, for example, some additional equipment, the tools installed in the well. So we need to know the exact composition in the future, for example, at that depth. We have initial composition, equation of state, and so on. Which experiment is the best, the most suitable for that CVD, right? Or
yeah, so you have a composition after some depletion in the reservoir?
yes. No, we have initial composition.
Yeah.
And using that initial composition, we need to know the composition in the future, right? After some depletion.
Right. So that would be the CVD.
CVD doesn't matter if we need to know the composition in the reservoir or inside the well, because in the well there are different processes. I mean, the gas, the segregation, fluid segregation, and so on. Doesn't matter, right? Just CVD.
Yeah. So what if you're talking about in the well bore, right?
Yes.
Yeah. So then I would just take the CVD removed equilibrium gas, and then flash that at pressures and temperatures within the well bore. And that would give you the liquid dropping out at those a little bit lower temperature or pressure. But what you'll produce into the well will be very similar to the CVD gas.
Mm-hmm.
And then how it splits in the well bore would depend on pressure and temperature, but using that composition.
Mm-hmm. So CVD, right?
CVD to get the estimate of what is the composition entering the well bore at a given average pressure.
Mm-hmm.
Yeah.
Okay, thank you.
Sure.
Okay, so now we jump to the next slide. Yeah, so the list of the different PVT, the conventional lab PVT experiments that we're going to discuss, we have the CCE, CVD, DLE, and the separator test. And these three experiments on the top, these are conducted at the reservoir conditions. So the data that we get from these experiments help us tune the equation of state model to the K values at high pressure and temperature. So if you remember the tip of the nose, so that is convergence pressure. So in that region, we try to tune our equation of state model because that's relevant for the reservoir condition. And then the separator test help us tune the K values at surface, low pressure and temperature conditions, because we get these measurements at low pressure and temperature, which represents our surface process. The important aspects that we are going to discuss for the different PVT experiments is like how the different PVT experiments are conducted, so the lab procedure there, what are the different measurements, and what are the different reported quantities for each experiment, and we will touch upon different uncertainties in the different PVT measurements. So first we will talk about this constant composition. So that's the most common PVT experiment, and it's conducted for both oil and gas condensates. The reported quantities that you see in the PVT report, and we will look at the tables from the PVT report as well. What reported quantities we have from the CC experiment for the two reports we are using in this course. So the first one is the relative total volume. That's this, and that's usually represented as PRT. We will look at it, what it is in the coming slide. We have the bubble point, dew point pressure, single phase density. So if it's a gas condensate, then the single phase gas densities. If it's an oil, then single phase oil densities. Undersaturated gas Z factor. So that's only relevant for the dew point samples. We have the gas condensates, isothermal compressibilities of the undersaturated oil, and we have this oil relative volume, which we generally represent as VRO. And we will also look at those, what do we mean by VRO in the coming slides. How the experiment is done, it's very, very simple. So you take either you have a bottom hole sample, or you have a separator oil and separator gas samples recombined together to create the well stream composition. And we take those either bottom hole sample or the recombined sample into the PVT cell. So we have this ZI, that's our total composition. And we have a constant mass of that composition that we have put it into the PVT cell. And we start the experiment at pressures higher than the saturation pressure at the given temperature. And then we just start increasing the volume or decreasing the pressure. So that's like this P2 is lower than P1, but it's still higher than the saturation pressure, and the temperature is constant, and we are not removing anything. So it's just the expansion of the fluid that's in the PVT cell. And we reach to the saturation pressure, which can be either a bubble point or a dew point. So if you have a bubble point, then you see this incipient phase or the equilibrium gas phase coming out from the top because it's lighter. And if it's a dew point sample, then you see the condensation going on, and then you see this liquid phase at the bottom, the liquid droplets coming out from the bottom. So that is gonna indicate the saturation pressure of the system, and then we just continue expanding the PVT cell, and then we have two phases now, the YI and XI, the equilibrium vapor phase and the gas phase. And then we just measure the individual phase volumes. And so the oil volume and the gas volume. And we also measure the total volume of the PVT cell at any given pressure. Yeah. So the measurements done. So you get the total cell volume at any given pressure. You get the individual phase volumes at given pressure. So the volume of the oil and volume of the gas phase. And this is only possible to measure if you are using a visual PVT cell. So there are two types of PVT cells used for CCE. One is called the blind cell. Blind cell means that you cannot see the individual phases or the interface of the individual phases in the PVT cell. So there is no window through which you can see. And there you can only measure the total volume versus pressure. But if you have a visual cell, then you have this leverage of measuring the individual phase volumes. And now most labs, they use the PVT cell, the visual PVT cells. The saturation pressure. So the saturation pressure, it can be measured from the discontinuity of the total volume measured versus pressure data. And this is generally for the blind cell. And what do we mean by that? So if we look at this figure here, which is this volume or the total volume of the cell versus the pressure, and there are different fluid systems. So we have A, which is representing a very low shrinkage oil. So you see a very small compressibility of the single phase oil. And then there is a very drastic change in the compressibility after the bubble point, because now the gas is coming out, and the total compressibility of the system has dramatically changed, and the volume is exponentially increasing. So that's one fluid. And then we have fluid B, which is more kind of more volatile oil. And then we have C, which is more near critical fluid. And then D is the gas condensate, where we have a dew point instead of the bubble point. And what you see that if you have a low shrinkage oil, then there is a clear discontinuity in the total volume before and after the bubble point. And here you can accurately measure or predict and calculate the bubble point from the discontinuity on this curve, the total volume versus pressure. So if you use the blind cell and it's a low shrinkage oil, you can get the bubble point with good accuracy. But you can see that if the oil is if we have a high shrinkage oil like volatile oil or near critical foods or gas condensate, it's almost impossible. It becomes almost impossible to accurately get the saturation pressure from only this information, the total volume versus pressure data. So that's why these blind cells, they generally only work if you have very low shrinkage oil, which like usually like the GOR of less than 500 or 300 SCF per barrel. But if you have high GOR fluids, then you need this windowed PVT cell to get the measurement of the saturation pressure. Okay, now we see what are the reported quantities. So if you look at the CC experiment table, what we will find out that you generally have a pressure, you have pressures, and then we have this relative total volumes reported, and by definition, the relative total volume, this VRT here, is the total volume of the PVT cell divided by the volume at saturation pressure. So the volume at this pressure here. So that's why the than 1 for all pressures higher than saturation pressure and it is exactly 1 at saturation pressure, and it's greater than 1 at all pressures higher than the saturation pressure. And then you have single phase densities here, which is simply the mass in the PVT cell. So since we have done the recombination and put the mass in the PVT cell, so we know how much mass is there in the PVT cell, and we have the total volume measured at each pressure. So that will be the function of pressure, the total volume, and you get these densities at each pressure, and that will represent the single phase fluid densities at all pressures higher than the saturation pressure. Gas Z factors only again relevant for the dew point samples. So you get these gas Z factors also for the gas condensate reservoirs, for example. And then this VRO, which is the relative oil volume, and that's the oil volume divided by some reference volume. And we will see what are the different reference volume used in the PVT lab to define the VRO curve. Yeah, so I guess these are like, so single phase gas Z factors by definition is the gas volume, the real gas volume at the given pressure divided by the ideal gas volume. The real gas volume is the same as the total volume at all pressures higher than the dew point. And the ideal gas volume is simply from this equation PV equals to nRT, where we know the moles of the gas PVT cell, and we know the pressure, and you just calculate the volume. The compressibility, and that's only reported for the oils generally, and the single phase oil. And we saw this expression, the compressibility oil in terms of the derivative, and then when the labs usually, when they report the compressibilities, they report they approximate this derivative with some kind of finite difference operator. And here this pK, that should not be confused with the convergence pressure. So that's not the convergence pressure. Maybe we should use some other nomenclature here. But this is not the convergence pressure we looked at in the K value plot. So this is the pressure at stage K, for example, because now since we are talking about experiments, we had different stages, and K represents one pressure stage, which is mentioned here. Yeah, so that's something we have already seen, so there is no surprises here. Yeah, so now we'll talk more about the oil relative volumes, which is the oil volume divided by the reference volume. Measurements are only possible with the indoor PV cell. We have discussed this before. You need an indoor PVT cell to get the VO. Now, there are actually two different types of the VRO values you may find in the PVT report. And actually in the PVT report we have, you will see what are those numbers. But there is one VRO that's where the reference volume is the saturation pressure volume. So the volume at the saturation pressure, that's this guy here. And then there is another VRO where the reference volume is the total cell volume, which is changing with respect to pressure. So here it's constant, here it's changing with pressure. And generally this one, we like to call it liquid relative volume. And this is generally, we call it the liquid saturation, because this is with reference to the total volume, the PVT cell, or the total hydrocarbon volume. So now we will see the differences. So if we plot this VRO curve for a bubble point system, so if we plot this one, this guy here, this number 2 VRO, so that's our VRO 2, and this is VRO 1. That's this one here. So you see that VRO 2 should be equal to 1 until the bubble point, because the total volume and the oil volume, they are the same. So it should be 1 until the bubble point, this blue line, and then it starts decreasing sharply because the total volume starts to increase exponentially with the decrease in pressure. So because the gas is coming out. Now, if you look at this VRO1, so that is exactly equal to 1 at the saturation pressure. But as we go above the saturation pressure, it is decreasing depending on how much is the compressibility of the oil, because Vs is now the constant, which is the maximum oil volume you can get, which is at saturation pressure. And then as we go at higher and higher pressure, the oil is compressing. And this line here, it indicates the compressibility of the oil. And after the bubble point, again, this VRO starts to decrease, but not as sharply as this one, because now this number here, the denominator, is a constant value. And this curve here mainly represents the oil shrinkage against the constant reference. And if you look at the same figure for the gas condensate, so it will look like this, for example. So we will have a higher VRO from this one, from the one. So that's VRO again 1, and then this is VRO 2. And you see that the VRO 2 is smaller than VRO 1, again because VT is higher than VS at pressures lower than the dew point. Above the dew point, there is no oil volume, so the VRO is 0.
It seems like it's more clear where the saturation pressure is for the option 1. Is that the case, or are they equally?
It's more what?
More sharp. Or like it seems like it's more clear where the saturation pressure starts. For the pink curve.
For the gas condensate.
Well, I guess for both.
No, it's clear with both curves. So because like for the oil, if you see it's exactly 1, and then it starts to drop at the bubble point.
There was a question or a comment there?
What is the comment? I don't see any answer.
The angle between VRO2 and VRO1 is the compressibility.
Yeah, that's right. So this curve here, this is representing how the compressibility of the oil is changing at pressures higher than the bubble point. And you can also see it from this. If I plot, for example, this VRT versus pressure. So that's the relative total volume, and again, relative total volume, that's just the volume in the PVT cell divided by the saturation pressure, and we know VT is equal to VO. That's VO at pressures higher than the saturation pressure. So if I plot the same this guy here, so then it will also be look like this, and then you will have a sharp increase after the bubble point. So this is again representing this line. This will be similar to this line here, again representing the compressibility. Okay, any more questions? No? Okay, and one last comment here. So yeah, you can actually, if like for example, if there is no VRO, for example, if there is no VRO in the PVT report, and if you only have this VRO in the report, PVT report, then you can calculate the other one with this simple relationship. So VO over VS, that's this VRO1, that's simply equal to VO over VT, which is this VRO2, so that's your VRO2, times the VT over VS, that's your VRT, the relative total volume. So you can simply calculate this one from the other. And usually, yeah, why we are showing this is because some PVT softwares, they only have the option of inputting, for example, only VRO1, or some have only option of entering VRO2. So you can actually calculate one from the other if the one is missing in the PVT report. Okay, so now we can just look at the PVT tables that we have in our PVT report. So we have a black oil sample, and the CC experiment actually looks like this. So now we can see what is what. So this is our pressure, and then again this experiment, so it has the saturation pressure of about 2000 psi. It's a very low GOR oil. It has a very low bubble point, and it's highly undersaturated. We have a reservoir pressure of 7500 psi. So this is V liquid over V total. So that's our VRO, and this is the VRO1, I guess, the one that we saw before. I think so. No, that's 2. Yeah, it's easily forget. How do you? Okay. Yeah, so that's VRO2, and then this is our VRO1, and you can see it from the values also that is not equal to 1 or 100% above the bubble point. This is relative volume, that's VRT. The relative total volume, and this is density compressibility. And then we have a gas condensate, which is kind of energetical. So we have pressures, and then here there's the saturation pressure is very close to the initial reservoir pressure. So it's slightly undersaturated. And then again we have V liquid over V total, that's our VRO2, VRO1, and then we have this relative total volume, single phase density, and gas Z factor. So that's the CC experiment. Now we can talk about a little bit about the data uncertainty, and so saturation pressures usually, and all the numbers that we are gonna show here, these are just the rule of thumb. Like these are not the absolute values in the errors. So like saturation pressure, usually there are plus minus 1 to 5%, but sometimes it can be very high, especially like if you have energetical fluids or very lean gas condensate, where it's not very easy to see when the liquid starts dropping out in the PVT cell. the uncertainties in the VRO measurement, the relative oil volume, it varies very widely with the type of PVT cell used. So there are different kinds of PVT cell available in the market. You have mercury-based cells, you have mercury-free cells. You can have these automatic measurements of the interface with time. So yeah, it depends what type of PVT cell you are using, and also the fluid system, of course. Like in near critical fluids, for example, you have a very rapid change in the oil saturation in the PVT cell with just few psi drops in the pressure, and of course the calibration of the PVT cell is always important to get the accurate measurements of the oil relative volumes. And the gas Z factors, yeah, +1 -5 to 5%, and we already have seen how you can QC the gas Z factors in the exercise we did yesterday using the standing card Z factor values. Single phase densities, usually, yeah, ±1 to 2%. We expect that error. And this is just usually what you also see sometimes in the PVT report, that they report this Y function. So this is just showing what is actually the Y function. Like usually what happens that when PVT labs, when they do the measurement of this relative total volume, the VRT, they try to smooth the data with some kind of with a smoothing function. So Y function is just a smoothing function to smooth the VRT pressure data. So Y function is represented as the saturation pressure minus the pressure, which is always gonna be less than the saturation pressure. And then you have the pressure again, and then the VRT -1, and they just plot the raw lab measured data of this Y function with respect to the pressure, and it starts from the saturation pressure and lower. And then they just fit a straight line through that because and just smooth this VRT data using this straight line. So this exercise, exercise 5, we are not gonna do because it's very simple and straightforward, and since we are gonna provide the solution, and it's just plotting the lab data, the calculating the Y function and plotting the Y function versus pressure and see how smooth the data is, and you expect that the lab data will be very smooth. So yeah, so we can just skip that exercise. But if there are any questions related to this experiment, that's the most simple experiment we have in the PVT lab report, and if it's done very accurately, because it since the composition is fixed, right, and you don't have any uncertainties, because your uncertainties usually starts coming from like the complexity in the experiment it starts to add when you start removing stuff. So then you have uncertainty, okay, how much you have removed if you have measured the removal accurately. So in this experiment, it's very simple. There is no removal. And if it's done accurately in the PVT lab, it's a very good experiment to tune the PVT model. But of course, when there is no removal, then there is very limited QC of the PVT experiment because you cannot do any kind of material balance. And you just have to believe that the lab has done the measurement accurately, and they should try to see how the equation of state model predicts the data, and with that you try to see that how the data quality is.
Question?
In essence, the Y function is a compressibility function. I don't like it's the compressibilities that we were talking about. Is the single phase compressibility of the oil, and that's only relevant at pressures higher than the saturation pressure. And Y function is only plotted for pressures lower than the saturation pressure, because we have this term here and you will start getting negative values of Y. So it's not relevant for pressures higher than the saturation pressure. It's only relevant to smooth the VRO data at pressures lower than the saturation pressure. I don't know if that answered the question.
I thought I mean, it is a compressibility function because it's mainly applied to account for inaccuracies when they take volumes from the cell when they calculate relative volume.
When they calculate the relative
In the laboratory, yeah. So yeah. I mean, some of the volumes will be lost in a way. So and you would need to account for effect of compressibility or loss gas volume to smoothen this curve, like you said. But in essence, it is a compressibility function.
But when you're saying that the some gas volume will be lost, so what do you mean by that? Because we are not removing anything from the PVT cell here.
Of course, there will be inaccuracies in the volumes that you measured.
Yeah.
In the
So if there are any accuracies in the total volume, yeah. So that's what we are correcting for here. And I think with these modern tools that we have now, this total volume measurement should be accurate, and you would need very small smoothing. I don't know if the labs are still using this function, because normally in this modern PVT reports we don't see this Y function anymore. So if we have any lab person here, maybe he can comment on this.
You know,
There's a commentary.
Yes, normally in our lab, it just maybe we should report it and not report it. And many labs don't report it anymore. I don't know that anyone using that value.
Yeah.
So it's more or less something. The quality of the sampling. It's difficult to get the straight line without waiting very long time for equilibrium just to get it. So, but I don't know that anyone using that value for anything. So that's maybe why labs don't report it anymore.
Okay.
yeah, I mean, clearly anything that's related to the pressure volume, changes. In this case, it's a two-phase system. The gas compressibility is maybe dominant, but in that sense, you could call it a compressibility related factor or function. But it is really a smoothing. And I think the comment that it's related to smoothing required because complete equilibrium at each pressure stage is not easy, and it's a time dependent factor. And so scattering that data is also implying there's some maybe insufficient time being used by the lab to reach equilibrium at each stage. And that's something they maybe don't really want to share as well, or maybe it can give them a guideline for new requirements on waiting long enough. But I don't think anybody uses it as a quantity for engineering calculations directly.
I can, for instance, I can say if I don't get a straight line and I try to smooth it just to do correction for my pressure, sometimes I just have to change my recorded pressure by 0.1, 0.2 or something like that. And definitely out of the range of the pressure transducer at all. Yeah. So I don't know, actually, this is maybe something maybe Curtis know about that. That is maybe something that's hanging for a very long time ago. I don't know.
Yeah.
Yeah, that sensitivity to the pressure, I wasn't aware of, but I think it's something that can be looked at. But again, it's really something that was used as a smoothing technique in the old days, and to get the VRT data probably more correct and smoother for sure. because the VRT itself has kind of a 1/P behavior, and it's not so easy to smooth. Obviously, with a straight edge ruler, doing this is much more straightforward for smoothing. So, yeah. But
and
okay.
any idea what the this plot will look like if you compare in contaminated and uncontaminated?
Well, my main saying is, why speculate when you can calculate? So I suppose if I or you wanted to answer that, that would be the simplest way to do it. I really don't believe it's that big an effect, because the contamination is affecting the oil volume, and I think this term is dominated by the total volume, which is increasingly gas. But I could easily be wrong. I'd want to do the calculations to check that.
Yeah. So I think we can get started with the next experiment we have on the list. And yeah, so now we will talk about this multi-stage separator test. That's the second experiment we have on the list. And so a little bit on the history. So originally, this test, the multi-stage separator test, it was designed for reservoir oil to provide a basis for converting the DLE data from residual oil to stock tank oil. And this is something we are gonna do. Like we will do an exercise on this DLE data correction. So historically, what people used to do is they used to have this DLE experiment and a multi-stage separator test experiment done on the oil, and then the separator test experiment was used to correct the DLE data so that you can use that data directly as black oil tables in your simulators, for example, like for material balance calculations and other things. And like the reasons why you need the corrections on the DLE data, that's something also we are going to discuss in this presentation. But now people have started also doing the same experiment on the liquid-rich gas condensate reservoirs. And again, as I mentioned earlier, that you have to be a bit careful when you are doing these experiments on condensate reservoirs. Then reservoir should be rich enough that it gives good enough separator oil volumes that can be measured accurately in the lab. The measured PVT properties that we have from this experiment, number one is the oil volume at the saturation pressure. So that's another important comment, that the experiment, it starts usually the saturation pressure. So you get the estimate of the saturation pressure from the PVT experiment, and you need to know the volume at that saturation pressure that you have put into the PVT set. But it's not necessary that you start the experiment at the saturation pressure. You can start it from some higher pressure, but usually it starts from the saturation pressure. And then you also measure the separator oil volume at each stage of the separator. So if you have multi-stages, like 1 stage, 2 stage, 3 stage separator, then we measure the equilibrium oil volume at each stage of the separator. And then there is the removal of the gas phase, because this is the multi-stage separator test and the DLE experiment. They are identical, except that in the multi-stage separator test you have different temperature for different stage, and DLE you have the constant temperature at reservoir temperature. So there is also gas removal. So we measure the gas volume that's released from the PVT cell, the gas gravity, and also analyze the compositions of the gases that are removed, which represents the separator gas composition. And then we also measure the final stock tank oil volume, the density of the stock tank oil, and the composition of the separator oil. The calculated properties from these measurements are the formation volume factor. So the formation volume factor, that's you have this oil volume at the pressure, the given pressure divided by the stock tank oil volume. the surface oil volume, and then you have the GOR, which is we will see there are actually two kinds of GOR that can be reported, and we will see what are those two definitions of the GOR that are usually reported in a separator test. So this is a good picture showing how the test is actually conducted. So we start with a total composition. We, yeah.
Not matching here.
It's the same slide that we see.
But you're not sharing.
Ah. But which it's sharing this, must be sharing this screen.
No, just up.
It must be sharing this screen, yeah.
Go to that.
Maybe this is it.
But this is the opposite. Keep that. And then just yeah, let's just try it. Stop sharing and then share. Excuse me. Let's try one more time. Yeah. Good.
Yeah. Okay. Yeah. Sorry for that. I didn't realize that it's the screen was frozen. But I don't know how much we have lost here. Yeah. So I went through this slide, and yeah. So these are just that's highlighting what are the measured properties, and then what are the calculated properties. So now we will see them in more detail here on this slide.
I'm good.
Okay, thanks. So yeah, so the way the experiment is done, so we have the PVT cell, and then we have the total composition, the mass and moles of the total composition in the PVT cell at the reservoir temperature, and at reservoir temperature, and we start usually from the saturation pressure, and then we should know like how much is this the volume at the saturation pressure, which could either be the gas volume at the dew point if it's a gas condensate, or the oil volume at the bubble point if it's an oil reservoir, or if it's an oil sample. And we just take that sample and then flash it to some pressure and temperature. So, and that represents our first stage separator pressure and temperature. So that's these two guys in this PVT cell. And so at that pressure and temperature, we expect to have two phases. It's independent of whether it's a dew point or a bubble point. You will get two phases at the first stage separator. So the separator oil, the gas will represent the separator gas. And then what we do is we remove this entire gas volume at this separator pressure and temperature. So that's the volume of the gas being removed. So delta VG1 is the surface gas volume from the first stage separator. We measure the composition, we measure the gravity of the gas from the first stage separator. Then we take this equilibrium oil volume and flash it to another separator pressure and temperature that represents our second stage. And again, because now this PSP2, that's the second pressure, is lower than the point pressure first stage separator oil, so you will again get two phases. And now here, relatively, you will get more oil compared to gas, because here it's you have already removed a lot of gas from the well stream composition, and now this oil will have low GOR. So you will get a relatively lesser gas here, and you will have oil volume. And then again, we measure the oil volume at this separator condition, remove the entire gas volume, and measure how much gas volume we have removed, and again the compositions and the gravity of the gas. And then we continue until we reach the stock tank condition, the surface conditions we have, and here again we will get a little bit of the gas volume, and we also have this will be our last stage, which is the stock tank oil volume. So we also measure the stock tank oil volume, the density of the stock tank oil, the API. Yeah, so the API is actually a function of the density, the molecular weight of the flashed oil, the stock tank oil, and the position of the stock. And the total gas that has been removed at the surface, that can simply be the sum of all these three gas volumes that are removed. And for this type of experiment, you can also use a blind cell or a windowed PVT cell, because what we are doing at each pressure stage, we are removing the entire gas phase and just keeping the equilibrium liquid. So if you are using a blind cell, and even if you cannot see the interface of the equilibrium gas and liquid, you will know when this interface of the liquid reaches to the top or the outlet of the PVT cell by just looking at the pressure gauge. Because like if I make a pressure gauge here, and then let's say when we will be removing this the equilibrium gas phase at constant pressure, the gauge pressure, this gauge pressure will, the indicator will be like this. And as soon as we reach, as soon as this interface reaches to the top, and there will be a sudden drop in the pressure as the liquid will start to go out, and you will eventually suddenly see that pressure going down because of the compressibility chain, and then you can just close the valve. So that can also be done with the blind cell. And in the past, this DLE experiment or separator test experiment used to be done with the blind cell, but now most PVT labs, they are just using windowed PVT cell, and they can just do it with that PVT cell. All the experiments, CCE, CVD, DLE, and multi-stage separator test. Okay, we can just look at the reported quantities that we usually see in the PVT reports, and so we have again the pressures. We start again from the saturation pressure, usually can be a bubble point or a dew point, and then we have different separator pressures, different stages. We can have until stage M, for example, and then we have the stock tank condition, and then again the temperatures are usually varying, but the different stages starting from the reservoir temperature at the bubble point or the dew point, and then at each stage we may have different temperatures, and then finally we reach to the stock tank temperature. Then we can have two kinds of GOR. There can be two different GORs reported, and you can see are the definitions of those two GOR. So the GOR1, that's this one here, at any pressure stage K is equal to the surface gas volume released at that pressure PK, pressure stage PK, divided by the stock tank oil volume. Okay, so it's just a matter of what reference volume we are using. So here the reference volume is equal to the stock tank oil volume, and in this one the reference volume VREF is equal to the separator oil volume at that given stage. So it's very similar to the 2VRO definition that we saw before. So you can have a GOR as a base on the basis of stock tank oil barrel, or you can have a GOR reported on the basis of the separator oil barrels at that given pressure stage. And yeah, and then this BO, this is just the oil volume at the separator conditions divided by the stock tank oil volume. That's why here it is equal to 1, because the oil volume is equal to the stock tank oil volume. And then we have the densities. of the oil phase. So here it will be the bubble point oil density. For the dew point, it will be there will be no oil density, because then we will have only the gas density at the dew point, and we will have the oil density at all these pressure, and this is the measured density at the stock tank oil, and all these densities at higher pressures are usually calculated from the material balance that we will see later on. So this is the only measured densities usually in a separator test or even in the DLE test. And then we have the gas gravities. So we are removing the gas and measure the gas gravities. We also measure the compositions of the gas, and if it's a dew point sample, then the total composition is equal to gas composition. At the oil, we have the total composition equal to the oil composition, and we generally don't measure the equilibrium oil composition at different pressure separator pressures. We only measure it at the stock tank condition usually. Okay, so yeah, so again, more on the reported quantity. So that's something we have already discussed. What is the BOSP, the oil formation volume factor from the separator test, and it is equal to the bubble point oil formation volume factor at the bubble point. And that's also something we can show that the two different, like if the lab has reported one GOR, for example, if the lab has only reported GOR2, you can calculate the GOR1 using GOR2 and using the oil formation volume factor from the PVT, from the experiment. Yeah. And then this is the oil density. So you can calculate the oil density from this expression here at any given pressure stage. Knowing so I said that this is the measured density. This is you measure in the PVT lab usually, the surface oil density or the stock tank oil density. And then we have the air density, the gravity of the gas at each stage, and then we have the GOR, measured GOR, and then the oil formation volume factor. And this is just the material balance equation. And if you, I think, yeah, and this is how it is derived. So there is the derivation shown here. So that's the mass of the stock tank oil volume. That's the mass of the total gas release, the surface gas release. That's total mass of that, and that's the at pressure and temperature, like for the given stage. So so that's the mass, and this is the total mass of the gas released until the pressure stage K, which is here. So yeah, so that's just a simple material balance. Yeah, and then if you will look at our PVT report, so that's how the table looks like. We have only the separator test for the oil sample, starting from the saturation pressure, which we saw it was about 2000 psi, and then we have used the same separator conditions as we have in the gas condensate PVT report, 300 psi, 100 degree Fahrenheit, and then we have the two GORs. So this is the GOR1. You see the units. It's a stock tank. It's a standard cubic feet of gas, of separator gas, divided by stock tank barrels of oil, and this is a standard cubic feet of separator gas divided by the separator oil volume. The separator oil, the formation volume factor. This is our BOB, the oil formation volume factor at the bubble point. We have the gravity of the removed gases and the oil densities. So this is the density of the oil at the bubble point. And it should be the same as the density of the oil from the CCE experiment. Let's see.
Here's that question from Geraldo.
Yeah, Gerardo.
Yeah, just a question on the flash quantities. Is there any specific guideline on the timing we should allow these pressure steps to take place, or do you take diminishing times because you know that the fluid in the cell is less volatile as you go through the pressure steps? And what is the recommended approach that you would have?
You mean the time that should be given to the fluid to equilibrate?
Yes.
At each given pressure, yeah. I think it honestly, I don't know how. I think it varies from one lab to another. How much time do they give for the equilibration? And like, for example, if you just look at the CCE experiment, and you may find out that like CCE experiment can have 20 to 25 pressure stages, and if doing that experiment, I don't know how much time do they take to complete one entire experiment, but yeah, like for each pressure state, I don't think it's a lot of time that's given for the equilibration. Gerardo? Yeah, Hans.
Yes, it depends a little bit on what kind of PVT cell you have, how long you have to wait for equilibrium. We have a sufficient mixture in our cell from Sanchez, and if you are going into 2 phases and we are just set up the mixing for the to get the gas out of the solution. After, and if you are using an CME, for example,
yeah,
I just have to put on the mixture, and if I wait 10-15 minutes to get equilibrium, then it's sufficient for each stage, because I have just do some experiments that if I wait 50 minutes or 1 hour, it's approximately the same. I have only maybe 0.1 bar expansion in the pressure before that, but it's important to wait about 50 minutes. It is with our cell, but it depends on what kind of PVT cell you have, how long you have to wait for equilibrium.
But I guess it may also depend on what kind of fluid system you have.
Of course.
Okay.
Yeah. So.
Yeah. Thank you. Yeah. That's appreciated. Yeah.
Thanks. Thanks, always nice to have some PVT lab guys in the courses, so they can just share.
Can correct the theoretical side of it.
That's what we are experiments, and theoretical is theoretical. It's also been difference because you have uncertainty in experiment. You don't have uncertainty in calculations and so on. Yeah. Oh, you have uncertainty, but you always get smooth curves. You always get straight lines and everything.
Yeah, that's right. Okay, yeah, and also in the same PVT report, you will see that we have the gas compositions measured for the different removed gases. So the gas removed at 300 psi separator pressure, like we have 14.7 psi, 47 octane oil composition. So it has about 93 mole% of the C7 plus. Okay, so yeah, this is just another example of the multi-stage separated test data, and I think it's this is taken from the monograph, I guess, this table here. Yeah, table 6.7, and here you can see like the experiment is done with different separator configurations. So the first experiment is done with the first stage separator pressure being 50 psi. PSIG here is done then 200 PSIG, 200 PSIG, and 300 PSIG. the temperature is kept constant, and then and the main reason why the different separator pressures were tried, I guess it's because they just wanted to see what's the optimum separator pressure, the first stage separator pressure, and you can see for example, from the GOR, like we will have to calculate the total GOR for this case, but I guess yeah. So I think this GORB, if you look at in this note here, so that's your absolute PSI per barrel of oil at indicated pressure. So that's your what is this delta VG at given pressure divided by the VOSP, and this is your delta VG that we saw before divided by the stock tank volume. So if we just use this GOR, because it's easy just to add these together to get the total GOR, because both are at the same reference volume. So if you just calculate the total GOR for the different separator configuration, we can see what is the kind of the optimum separator pressure here. Yes. So the first one is I think is 877. This one is 8 and 67, and then this is 0, 8, 0, 8 and 7, and this is 5, 9, 7. Okay, so 778, 768, 780, 795. So it seems like from this is the optimal pressure, because it is giving you the less GOR, meaning that more stock tank oil barrels for the same fluid, or for the same wedge stream composition. And you can also see that the stock tank oil is a bit more lighter, 40.7 API compared to these other values here. So it's more lighter, meaning that more lighter components end up being in the liquid phase. So yeah, so they will be sold as the liquid phase and not the gas phase, and that's what we want from the separator optimization, that we want as many components, as many moles of these lighter components as possible in the liquid phase, so they can be sold at much higher price in the liquid phase compared to the gas phase. And one other comment. So this is this is how it was done usually historically to find like the optimum separator pressure. But now, since we have this equation of state model development, like we usually develop equation of state models with the PVT data, so you can do all these separator optimization studies with an equation of state model and try to come up with the optimum separator pressure and temperature that you want to use for your field. And that's what Curtis was mentioning, that when for Rice method, the flat procedure, when Muscat and McDowell, when they introduced it in 1949, the main aim was to find the optimum separator pressure and temperature that can give them the maximum liquid yield at surface. So that can be easily done with an equation of state model. The quality checks for the multi-stage separator test. So one of the quality checks is calculating the densities. So as I mentioned earlier, that these separator oil densities, so the only measured density is usually the stock tank oil density. So that's this guy here. And then all other densities, the oil densities at all other pressure stages, they are calculated from the material balance. And so this is the equation that we saw before, the material balance equation. So yeah, so what we can generally do is we can calculate the oil densities with the same material balance and see if they coincide with the PVT lab report. So it's not a QC. It's kind of just replicating what the lab is doing and see if the FR values are consistent with the lab report. And then yeah, so another QC that can be done is the compositional material balance, and this, yes, Hans.
Yes, normally in our lab, before we take out any gases or something like that, after we have take out the gas from one stage in the MST, we measure if we have enough sufficient sample, we measure the density on the oil inside the cell. We're using the picnometer density. Then, if depends on if we calculated good in the beginning, we should have sufficient samples to do one measurements of density. If we have sufficient sample, we do that.
Yeah, so that's very good. Yeah, so that's like I don't know what other labs actually do, but what we have found generally in almost all our PVT studies, that almost all labs they just calculate these densities from the material balance, or maybe they measure the densities internally in the PVT lab, but when they report the densities, they just report it from the material balance, because then you don't see any deviation from the material balance, and they just make the clients happy. So, but like when you report the densities, do you report the measured densities, or do you do this internal check on the densities and then try to correct those?
Normally, I like to report measured. If I have measurements, I like the measurements.
Okay.
That's what I like to do.
Yeah. So that's what we should expect from all the labs. That if they can measure those densities, then the measured density should be reported, and in that case, this will be a very good QC overall for this volumetrics, then it will reflect the uncertainties in the BO measurements, for example, and the GOR measurements and the density measurements. Yeah, and if you have this deviation from the material balance calculated densities, then you know that there's something wrong in either of these three measurements. You may not be able to tell exactly what is wrong, but yeah, that will be some indication. Okay. Yeah, and then I was talking about this compositional material balance, which is because we know in this test we are measuring these YI values. So YI is also measured. That's the removed gas compositions. We also measure the stock tank oil composition. So that's our stock tank oil, and we are measuring the GOR values at each pressure stage. So we can calculate the number of moles of the gas removed at each pressure stage. And we can also calculate the moles of the stock tank oil that is present, which is the oil volume, which will come from our BO from the separator test, the surface oil density and the surface oil molecular weight. So we calculate the moles of the oil, we calculate the moles of the gas removed, and then we just apply a simple component material balance to calculate the total composition that was present initially in the PVT cell. And then we can compare this with the lab data, the lab reported total composition. So that's another QC of the multi-stage separator test.
The XOI?
Yeah.
That's using the lab.
Yeah, so that's measured. That's measured. Yeah. That's measured in the lab, the stock tank oil composition. Okay. Yeah. So now experiment, and yeah, the experiment is essentially the same as the multi-stage separator test, as I said earlier. It's only that the temperature remains the same, but there are a few other things to talk about this experiment. the reason why the experiment is usually conducted is to get this two-phase volumetric properties of an oil reservoir, meaning that you want to know, you want to know how the oil is shrinking below the bubble point, for example, and how much each pressure, and also the oil densities when the oil is in two phases. And again, the blind PVT cell can be used for conventional PVT measurements. Yeah. And this is another comment, like DLE does not replicate the performance of an oil reservoir. And I think everybody understands that, because in the DLE experiment, what we are doing, we remove the entire gas phase volume, and we ended up only having an oil phase in the DLE experiment in the PVT cell, and we just continue to deplete that and removing the equilibrium gas phase until we reach to this were standard atmospheric pressure where we have the residual oil. But still, we do the DLE experiments, and the main reason why we started doing the DLE experiment, I think again we just have to go back into the history that in the early times when there was not a lot of use of the equation of state models, then they generally wanted to have this data to use that the lab measured data directly as black oil tables. So in that case, what they were doing, they were just doing the DLE experiment on the oils, getting their BO and RS values, and then they knew that those BO and RS values from the DLE experiment, they are not representative of their reservoir because of this reason, that the DLE does not replicate the performance of an oil reservoir. And in that case, what they were doing, they were just correcting those values with some multi-state separator test, and then using those numbers as black oil tables in their reservoir models, for example. But now, since we have equation of state models, and now we can debate whether we need DLE experiments or not. But there are some upsides of doing the DLE experiment that we will see later on in the coming slides. And yeah. Yeah, so this is only generally done on oil samples only, and it has a similar procedure as the multi-state separator test, except that you have the temperature constant and it remains at the reservoir temperature. The number of stages can vary from 5 to 10 or even more if you like. Last stage is usually a bleeding process. So like usually this experiment usually goes until the standard conditions. So it goes until standard pressure. And this pressure, which is PN is usually the pressure just before, that's your last stage in the DLE, and that pressure generally, like this is the pressure just before the standard condition, and that may be usually like anywhere between 200 to 500 psi. So when we are going from 200 to 500 psi to stock tank or the standard condition, generally it's a bleeding process depending on how much pressure you have and how much gas is dissolved in the oil at that given pressure. And what do we mean by bleeding pressure? That's something we will also discuss later on. Oh, I guess it's the same slide, yeah. So what do we mean by bleeding process? And maybe Hans is here, so he can comment on this, like how they are doing this, like how do they do this, or how they tackle this situation in their PVT lab. But that's how it is generally done. So you have this Pn-1 pressure stage, which will be like, for example, let's say 1000 psi. And then you have a reservoir temperature. We will have two equilibrium phases, oil and gas, at that pressure. And then you remove the entire gas phase volume at constant pressure. You end up getting this oil again at 1000 psi, for example. That's Pn-1 or pressure stage. And then what we will do is we will just deplete this oil. So now this is our PN. So that is our 200 to 500 psi pressure. That's our PN. So this is that pressure stage now. And now we will just we remove this gas phase volume, and then like we will have to do some kind of bleeding process to go from like 200 to 500 psi to the standard condition. So the bleeding process is like you reach the maximum cell volume, and then you just you just open the valve, the bleeding valve of the PVT cell, and just you continuously remove the gas volume until you reach that standard pressure, because you cannot go higher than the maximum cell volume because of the large amount of gas that you will end up getting at the standard pressure. So that's why you need to do some kind of bleeding. So at constant pressure, at constant volume, which is the maximum cell volume, you just open the valve and then continue to bleed off the gas. And that's not the same as doing a single stage flash or going from PS1 to PN that we try to simulate with an equation of state model, and then going from PN directly to PSC with an equation of state model. So it's not that straightforward process, and that's something you have to account for sometimes when you have very high shrinkage oils or near critical fluids. If the DLE is done on those fluids, then you have to account for this bleeding to better or accurately predict the lab data. And that's we will see an example of it in the like how much difference it can make, this bleeding process in the PVT data that we get from the PVT labs.
That's correct. What you mentioned here, that's the way to do the DLE test. You have to bleed because of the limit of the cell volume.
Yeah.
Of course, you can run 50, 100 stages.
Yeah. That's
you can do it, but if you do 100 stages, because when you get lower and lower in pressure, you have to expand your cell volume very, very much.
Yeah.
So, and I think it does have no meaning to just get everything there. So when we come to the maximum there, you have to bleed down, as you said there. This is the only way to do it.
Yeah. So you have this constraint actually from the equipment side that you have to do it this way, and you actually mentioned the right like the correct way, like how you can correctly simulate with an equation of state model. So when you try to simulate this bleeding process for the last stage, you actually need to add more stages, more pressure stages between PN and PSC in your equation of state when you are simulating the PVT experiment with your equation of state model to replicate this kind of process. And it tends to predict better the last stage oil volume if you simulate the experiment like that. But usually it's only important if you have like very near critical fluids or like high shrinkage oils, because there you have a lot of gas and you have this complex phase behavior going on between the oil phase and the gas phase.
Yeah, actually the two main variables for when it becomes a problem or a big issue is light oil and high temperature. Yeah, it's basically that's where you'll start seeing big differences in the final atmospheric pressure volume of oil will differ substantially from the lab experiment versus doing a single flash from, let's say, 400 psi to 14.6 psi. The difference can be 5% difference, it can be 20, 30, 40, 50% difference if it's a high enough temperature and a light enough oil. And the reason for that is the light oil has more of its components in the let's say light heavy, C7, C8, and so forth.
Mm.
And the high temperature brings the K values of those components higher and higher, you know, because you've got this K value versus pressure plot, and it's got this 1 over pressure dependency in that pressure range. So you're moving those, if you flash in one stage, then you get those really high K values for C7, C8, C9, C10, and you move a lot of those components into the gas phase, stripping and shrinking that oil. Whereas in the actual experiment, doing it kind of differentially or a bleeding process is going to give much less shrinkage of that final oil. And the problem is that the PVT simulators, they just think it's a single stage, flash it from 400 psi to 1 atmosphere, and they always get this excessive shrinkage of oil, and that oil volume is the basis for the two main data from a DLE, which is BOD and RSD.
Yeah.
So it makes a big difference, but mainly for light oils and high temperatures, that gets worse and worse.
Yeah. Hans?
You said something I missed?
No, I thought you wanted to make a comment on Curtis.
No, it's okay.
Yeah, thanks. Okay, so yeah, so that's how that's the, like I tried to explain the bleeding process, why and when it is done, and yeah, and Curtis rightly mentioned that it's usually a problem for the when the oils are lighter and then the temperature is very high. And in the DLE experiment, like the last stage is actually the standard pressure and the reservoir temperature, and then we just cool that residual oil to standard pressure and standard temperature. So that's the residual oil that we get, and we analyze that for the composition in the DLE experiment. So again, the reported data. So you have BOD. So that's the oil formation volume factor from the DLE experiment. And the oil volume divided by the residual oil volume. So that's what Curtis was mentioning, that if you get this one wrong from the equation of state model, because you are not simulating this bleeding process, then all the BO values that you will get from the equation of state model will deviate from the lab data. So because it's just you are using this the residual oil volume as a reference. Yes, Curtis.
Yeah, even if you're predicting exactly the correct oil shrinkage from bubble point to the first pressure, and if you're getting an exact prediction of the correct oil volume shrinkage during the test, you'll calculate the wrong BODs, and then so it's even for a perfect match, you'll get seemingly wrong data. Yeah,
that's correct, and we will see an example of it how bad it can be if you don't include the shrinkage, for example. And then we have the RSD that represents the solution gas in the reservoir oil or reservoir fluid at a given pressure stage, and that's simply how much gas is removed from, again, JA is the final stage, so going from the final until the pressure stage PK, you just sum all the gas that is being released, and which will indicate how much gas is dissolved in the oil at that pressure PK, and then you just divide it by the residual oil volume. And again, the densities, so the densities again calculated from the material balance. You can calculate from the material balance, or as Hans mentioned, that you can also measure those densities, and that's what labs are supposed to do if they can do it. The densities to be measured in the lab. Yes, Hans?
I think it's more common that I don't measure it, and then I measure it, because it depends a little bit of the DLE. You only measure the stock tank.
Okay.
density because it's you have not sufficient samples during your experiment. So it's not possible because you normally to have many stages and you have to expand and to have a sufficient volume to expand in the volume of the cell. You can you have not so much stock tank liquid when you finish there. So in the DLE, you definitely not measure any densities except the stock tank density at the end, and then you calculate all densities. It's only.
But I believe like DLE should have more oil volume at each pressure stage because you are doing it on the oil and then.
Yes, yes, but you have to when you start the experiment, you have to load the cell with very, very small volume.
Yeah.
And if you take out some oil samples during your experiment, you will you will at last you will have no more oil to expand. So it depends how much oil you can put into the cell before you start the experiment, because for every stage, if you remove some of your equilibrium liquid, you have less to do the next step in your experiment.
Yeah. Hans, I have one more question that I had been dreaming of asking to some PVT or some lab guy.
Yeah.
And the question is that, like, for example, if I have an oil and if I do, for example, a CCE test, a DLE test, and a separator oil and a separator test, I will have independent measurements of the oil density at the bubble point. Like I will have one measurement, for example, from the separator test. will have one measurement or calculation from the DLE at the bubble point. I will have one from the CCE test. So if like what I have seen in almost all reports that all these three values are almost always identical. So there is no difference in the lab reported value. So what do you do like when you see the differences in the lab?
I said that I have discussed this with because in our lab we reported 3 different densities is actually what we are measuring. I know that service companies that's reporting to us, I don't mention any service companies, they decide that one of the they normally they're doing what they call the Anton Par high pressure density measurement. This is most accurate, and they said this is the true value, and then they tuning or something like that everything matching that, and that is not correct. And when we are doing it, we're doing a one measurement because we are using the DLE, and we are taking the stock tank oil density, and then we're back calculating the density to the saturation pressure. And with the multi-stage flash, we're doing the same, and from the single flash, or for the CME, we're doing the same. So then we are reporting 3 different densities.
Okay.
Taken from the experiment. And if the laboratory just reporting one, I asking the service company why they are doing this, because we are measuring the Anton Par high pressure density. We believe in that that's the true value.
Yeah. But you can just imagine, even if that value, if they believe that value is correct, then like if you do this material balance on the different tests like DLE, separator test, for example, you will always see that they always are 100% on the material balance. So the material balance always closes 100%. That means that they should be manipulating some other data to match that density with the material balance.
That's my opinion. Yes.
Yeah. Okay.
That's my opinion. I'm working at the lab, and we know all the trick in the book that we can do. So I don't like it because I told them I don't believe you when you said that you get exactly this density 4 digits for all these experiments. I don't believe you.
That's right.
And I understand them that they told me that if you're reporting it, they get so many questions for reservoir engineers and why is it different? That's why they're doing it.
But thanks for answering the question. So that's something that was bothering me for a long time.
Yeah, so that's why they're doing it. So I don't know why, but I don't like it myself. When we report it, we report 3 different densities because there's still some uncertainty in all measurements of density. Even Anton Power is very accurate.
Yeah, that's correct. Very good. So yeah, continue on the topic here, the DLE. So we also have the gas Z factors reported because we have the gas phase at below the bubble point pressure, and that can simply be calculated from this material from the real gas law, PV equals to NZRT, because we know how much moles of the gas we have in the PVT cell at the given pressure and also the volume, so the moles can be calculated based on how much volume of gas we have removed actually. So yeah, and we also have the compositions of the gases at each phase, at each pressure, and then the gravity of the gas, and also we have the composition of the residual oil. And the quality check methods are essentially the same as the multi-stage separator test. Yeah, and again the Z factors, you can quality check standing card Z factor chart. I think we went through all these slides. So what are the measured properties and the calculated properties, and we will also see it. So we can see it here. So the labs, they report the solution gas oil ratio, that's RSD. We saw it before, and the units for RSD is SCF per residual barrel. So if it's written stock tank barrel, so that will be wrong because the DLE data have to be corrected to the stock tank condition. So this is on the basis of this residual barrel that we get at the end of the DLE experiment. And then we have the relative oil volume, that's the BOD, the oil formation volume factor. We have the oil densities, and that's something we were discussing before. So this is the density that is measured, and all the other densities are calculated from the material balance. And gas Z factors, and then the gas gravities are measured. And then this is for the compositions of gases at each pressure stage. So that's the first pressure stage below the bubble point. That's 1800 psi here, and then 1500, 200, and then in the last stage we have the gas composition, and we have this XORI, the residual oil composition. Yeah, so here we will just see some of the slides showing the importance of the So that's so this is for example, this is this is one from one case study that we were doing, and you can see so this is the oil volumes from the lab report, and this you can see this, and this is oil formation volume factor. So oil volumes and oil formation volume factor from the lab is the same because we are assuming 1 barrel of the residual oil. So this is the oil volume and the lab oil formation volume factor. And if we use the EOS model, and if we have the capability of calculating the volumes and not this oil formation volume factor, so that's something we can do with, for example, PhaseCom, because in PhaseCom, the way it's programmed, it can calculate all the physical properties that you can measure in the PVT lab. So you can simulate, for example, how much volume is there, how many moles, for example, of the gas phase is there, and moles of the oil. So we are calculating the absolute volume of the oil with an equation of state model at any given pressure and temperature. And then we are just converting these volumes to the oil formation volume factor, the same definition as the lab is using. So like dividing this number with this 0.883, which is the residual oil volume. So you get 4.893, similarly get 3.276, and you just compare them, and you see that you have these large deviations in the oil formation volume factor between the equation of state model and the lab data. And here we are not doing any bleeding, so we are just going straight from 200 to to the atmospheric conditions. And so now, so this is the case, the simulated case with the bleeding process now. So now, if we, so now what we have done here, so that's our last, like next to the last stage. So that's our PN in the DLE test, and then we have added artificially more stages until we reach to the atmospheric condition. So we don't have any lab data. So we don't have any data from the lab, but with the equation of state model, you can calculate all these volumes. And then once the bleeding process, now you see that the equation of state model and the lab data, oil formation volume factor, they are 100% matching, almost 100% matching here. Yeah. I don't know why I cannot undo the. Can I do undo? No. Okay. Yeah. So 4.275 versus 4.274, and you see it is matching almost exactly at the bubble point, and you have lesser deviations on the rest of the data. So here, for example, but this was like a very near critical oil. For example, you can see it from the oil formation volume factor at the bubble point. It was a very light oil, and the temperature is also relatively higher, so 114 degrees C, as Curtis said. So here it had a significant effect whether you include the bleeding stages in simulating the DLE experiment or not. Okay, very good. So, yeah, there are just important points. I think we have already discussed these things, like why we can do a DLE test, but just go through them one more time. So to get the volumetric data, the oil volumetric data below the bubble points, you get the densities of the oil phase. You also get the densities of the gas phase, and these are generally important for hypermobility reservoirs where you have gravity segregation. So you would like, in that case, you would like to have a very good match of your oil and gas densities with your, for example, equation of state model, so that this gravity segregation process is modeled correctly in the reservoir simulator, for example. Also, we get the measured the viscosities of the oil. And we generally have the calculated gas viscosities, which are a function of the composition, and usually there are some correlations being used. So one of them is Lee Gonzalez correlation, for example. The oil viscosities, they are not part of the standard DLE experiment, so you have to order them separately. But the experiment used for the oil viscosity measurements is essentially the same as DLE. So you remove the equilibrium gas phase and measure the oil viscosity of the equilibrium oil phase. The oil shrinkage at reservoir, so that's the function of this oil formation volume factor. And you also have the solution gas release, which is a function of how much the gas is dissolved, which is RSD. And these both actually give you in the simulator the saturation of the oil and saturation of the gas, which is actually driving your relative permeabilities, PRO and KRG values. And together with the relative permeabilities and viscosities, you get the mobility of the oil and gas phase, and that gives you the rates that you get, that you produce from the well. Yeah. So then we will talk about the data correction, the DLE data correction, and that's something we discussed briefly before, that the DLE data should not be used directly as black oil table, and you have to do some correction if you want to use that data as PVT tables, for example, or if you want to, for example, use BO at the saturation pressure from the DLE test as a BO value, for example, for your in-place volume calculation. Then you would like to do the correction. You need to do the correction using a separated test experiment. And the main reason is that the DLE PVT properties, they are not representative of the actual surface process. And because we have already seen that BOD and RSD, they are based on the residual oil volume. And the residual oil volume is not the stock tank oil volume that we generally produce and sell it. Because the way this residual oil volume is produced in the PVT experiment is different than how we produce the stock tank oil volume. Okay, and because this residual oil volume is produced during depletion, keeping the reservoir temperature high, but the stock tank oil volume is generally produced taking the reservoir oil volume, the equilibrium reservoir oil phase, and pass it to the surface process condition, and where we have a stock tank oil condition as well. Yeah, so this DLE data that needs correction, it can be corrected using some empirical correlations. There are many, and we will see some of them here. Like one of them for BOD, and the other one is for RSD correction. And the most recommended way of generating black oil tables is to use an equation of state model that's already tuned. So returning to my question about DLE, can DLE test be done for gas condensates? Yeah. Is there, and yeah, I guess you can speak out. Maybe, is there any specific reason why are asking the same question again?
No, it's not the same. I just wanted to know, because before I said it's gas condensate well, right?
Yeah.
But when the well is producing from the oil rim,
Yeah.
is it still CVD that is preferred here, or just curious? I just need yes or no.
Yeah. So if the well is producing from the oil rim and you have the oil sample, yeah. So that's something I think we will try to answer this question in slightly different way at the end of the presentation, like because when we started the discussion on the DLE, we said that the DLE experiment, though, if you look at the historically, the DLE experiment actually started like the reason why the DLE experiment was designed in this way is to get these volumetric properties of the oil below the bubble point and use them as black oil tables in the simulator. And for that, you needed the correction. So that's why you also needed a separator test together with a DLE to do the corrections. But now, now in the modern times, like when we are more developing equation of state models and use them to generate PVT models for us, like black oil tables or the pseudo-wise equation of state models. So now the mentality is, or the objective of having these PVT reports and measured PVT data is a bit different. Now you need this PVT data to tune a PVT model and use that to generate black oil PVT tables. And for that purpose, you need to see what are the advantages and disadvantages of doing, for example, a CC experiment versus a CVD and a DLE experiment. And if you have an oil, generally, like there are certain advantages of doing the DLE experiment, and there are certain disadvantages of doing that. Similarly, CVD experiment, that's like a general rule of thumb that for gas condensate, that's the go-to experiment if you want to simulate the depletion. For the oils, generally, if it's low GOR oil, like for example, 1,000 CF per stock tank barrel, generally, DLE experiment is usually done for that. But if you have volatile oils or gas condensates or like near critical fluids, generally the CVD experiment is recommended. But yeah, but we will also come back to these points of what are the advantages of doing the DLE experiment with respect to the EOS model tuning compared to the other experiments, and when you can think about doing that experiment on the PVT samples.
Okay, thank you. Thank you.
Okay, so the equations, so these are some empirical correlations that can be used to correct the BO and the RS from the DLE experiment. So that's from the DLE experiment. And then we are using this BOB. So that's your multi-stage separator test, the BO at the bubble point. And then this is also from the DLE test at the P equals to PB at the bubble point. So you calculate the BO, and similarly we calculate the RS, again using the same information. That's from the multi-stage separator test, and then this is from the DLE at the bubble point, and this is also from the DLE at the bubble point. And then you get the BO and the RS values that are corrected at the separator conditions, and then you can use these numbers as black hole tables. But we will see in the next slide when there is because we know that if you use equation of state model to generate black hole tables, that's the answer. That's the right answer. Okay, and then we can compare the results of these correlations with the black hole tables generated from the equation of state model and see when these corrections are okay or so, and when these corrections should not be used, and they make a large difference with respect to the black hole tables generated from the equation of state model. Okay, and this is yeah. So this is just a question. Try to think about it, and we'll see. Try to answer this question, like why, like since DLE, if you do the DLE experiment versus a multi-stage separator test experiment, we know that multi-stage separator test has certain number of stages, usually 2 or 3 separator stages, and DLE experiment is the same as the multi-stage separator test, but it has more number of stages. And usually, if you have a separator train, and if you have more number of stages, you get higher recovery of the oil. But what you will always find out that if you do a DLE versus a multi-stage separator test, even though the DLE has more stages, you will always get this BOD, which is from the DLE test, greater than from the BO from the multi-stage separator test, which is the BO from the multi-stage separator test, and which is the actual BO. And if you have higher BOD, it means that you need more oil volume from the reservoir condition to generate 1 stock tank barrel of oil. So you get less recovery of the stock tank barrel, even though you have more stages in the DLE. And I can briefly answer that question, and it's mainly because of the temperature, because in DLE you have higher temperature, even though you have more number of stages, but you keep the temperature high at reservoir temperature. And as Curtis was also mentioning before, that if you have higher temperature, it means that you have high K values of all these intermediate components that can be part of the liquid phase, for example, that can be part of both the gas phase and the liquid phase, for example, C4, C5, C6, C7 components. And if you have higher temperature, then those components will try to be in the gas phase compared to the liquid phase. So that's why in the DLE, because of the high temperature, you get more of these components in the gas phase, and you lose the recovery of the oil, and you get a higher BOD compared to the BO from the multi-stage separator test. Yeah, and this is the figure I was talking about, that when you think that this traditional corrections to the DLE experiment DLE data should be done. So this is a case of slightly volatile oil, and you can see, so this is the RSD, the RS from the DLE test, and this is about 1500 SCF per residual barrel. And if we use the equation of state model, so you can generate black hole tables with an equation of state model, either using a CCE experiment or a DLE experiment, and that's something you see here. So this is these are the points here, and these are overlapping, so you don't see the difference actually between these two lines here. So if you generate the black hole tables or this RS curve from the equation of state model, either using CC or DLE, it doesn't matter. And if you compare it with this RS curve that's coming from this traditional correction that we were seeing before, you see that it's under predicting the RS, slightly under predicting our RS, but there is not much big difference. And but if we go to the highly volatile oil, now you see, so now again, this is the RSD curve, and you see it's a very near critical oil, about 4500 RSD at the bubble point. And if we do again the predictions or the black hole table calculation with the either DLE or a CCE or a CVD test, you see that these are almost overlapping. So there is not much big difference in three of them. The DLE is slightly lower compared to the CC and CVD, and CC and CVD are always overlapping. But you can see that these traditional corrections are far removed from the correct answer. That's from the equation of state model. So this number here is versus this number. So for low GOR oils, you can do this correction, but for when we go towards the volatile oils or near critical fluids, then these corrections usually don't work, and then you are obliged to use the equation of state model to generate black hole tables. So yeah, so that's why it's always recommended to generate the black hole tables with an equation of state model with consistency. And even if you have low volatile oils, if you have low shrinkage oils, like low GOR oils, you may sometimes find out that these corrections will lead to negative values of RS and BO values. And that's something we have I think in the exercise. And we are not going to do the exercise because again, it's straightforward, just applying the two correlation, but I can just briefly show the results in the solved version so that you get the idea of what we are trying to do. Okay. Yeah. So here again, this is the BO and RS from the lab data from the DLE experiment for the oil sample. This is the RSB and BOB from the multi-stage separator test data from the PVT report at the bubble point. And then we are applying those two equations that we saw in the PowerPoint and calculating the BO and the corrected RS, corrected BO and corrected RS. And so what you see, for example, here, like for example, the BO value and then RS value. So you see that you have these negative RS values at the residual or at very low pressures. So yeah, because these correlations or these equations are just empirical, and then you may end up getting these negative answers. So that's why it's always safe and always consistent to use the equation of state model to generate black hole tables. And that's something we will see on day 5, how we can use equation of state models to generate black hole tables. Yeah, so I think, yeah. So we have this CVD experiment, and then we have an associated exercise. So we will just go through the theoretical part here about the CVD experiment, and then hopefully do the exercise tomorrow. It's an important exercise, how to QC the CVD experiment, and we generally emphasize a lot on that QC. So we will do it tomorrow. But is there any question related to the DLE experiment? Yeah. Okay, that's very good. So I think we just jump to the. I hope I don't have to reshare the screen again. That's very good. Yeah. So we just jump to the CVD experiment, and that's the last experiment we have on the list. And yeah, we briefly touched upon this before, and that's the most important PVT experiment for gas condensate reservoirs because it replicates the depletion performance, and it is designed to provide this volumetric and compositional data for gas condensate and also volatile oils, because in volatile oils as soon as you start depleting below the bubble point, there is a large proportion of the equilibrium gas phase that you start producing, and the CVD experiment is giving you the well stream composition close to that actually. Yeah. And actually for gas condensate reservoirs, we can use the CVD experiment to calculate the recovery of the surface gas and surface oil versus reservoir pressure. It also gives you the produced well stream compositions versus pressure. And you also get this the liquid saturation in the reservoir during depletion from the CVD experiment. Again, how the experiment is done. So we start again from the saturation pressure. We have the volume at the saturation pressure. So that's the first stage. And then we expand the cell. So we have two phases, oil and the gas phase. And then we measure the oil volume, the total volume. And then we just remove enough gas, enough equilibrium gas that we reach the same cell volume that we had initially in the PVT cell. So we always maintain the constant volume in the PVT cell. And when we remove the gas phase, we measure the composition. And usually, since it's a gas condensate reservoir, so you have some condensate associated with the equilibrium gas. So that's why when you process it at surface, when you flash this equilibrium gas at surface, you get two phases. You get a condensate phase, and you get an equilibrium flash gas phase. So this is your flashed oil, and this is your flash. So that's your flashed gas, and that's your flashed oil. And we analyze the two products separately. So we measure the composition of the flashed oil, and again you remember this nomenclature: O with a hat, meaning that surface oil coming from the reservoir gas phase, the G, and surface gas phase coming from the reservoir gas phase. We analyze these compositions. We also have the volumes of each of these phases, and then we just do this mathematical recombination to come up with the composition that is in the PVT cell. And that's what the PVT labs report at each pressure stage in the CVD experiment. This process here, it can be a very simple single stage flash process, or it can be complicated cryogenic flash, depending on how sophisticated you want the compositional measurements to be. So, like for example, because what this is in the CVD experiment, the most important data actually is the equilibrium composition, and that's something you want to measure very accurately, and that's why different labs may have different processes or different designs of the processes. And so, like for example, Core Lab, they generally use the cryogenic flash. And in the cryogenic flash, they have liquid nitrogen to freeze the freeze this equilibrium gas so that they can extract all the maximum amount of liquid that is dissolved in this equilibrium composition, and then so that they can they can calculate or they can do this mathematical recombination more accurately. Because if you just do a single stage flash, there may be chances that you lose some of the liquid, and that may condense out in the pipe from which the gas is flowing. And then if you will lose that liquid, then you will get an equilibrium composition that is much leaner compared to what you expect in your well stream composition when you start producing. Yeah, so that's how the DLE CVD experiment is done. So that's just one cycle, and then you continue the same cycle again and again until you reach to an abandonment pressure, which is usually less than 1000 psi, and then at the abandonment pressure you have the residual oil, XI, and at PN, and then you just do a single stage flash of that XI to get the composition of that residual oil. Regarding all these compositional measurements, we will go through them in more detail tomorrow. So there is a dedicated PowerPoint on the compositional measurements. So if you're confused about what is single stage flash and why are we doing it, so it will be more clear when we will go through that tomorrow in more detail. So the measured properties in the CVD experiment, we have the bubble point, dew point again. That's actually coming from the CC experiment actually. You have the liquid and gas volumes at each pressure state, similar to the DLE. You have the gas compositions, but here again, that's the most important data, and that's where the labs usually give more emphasis to measure it very accurately compared to if you have a DLE experiment. And then we also measure the volumes of the gas produced at each stage, gas factors, volume, composition, and density of the residual oil. Yeah, and that's something that's represented here. So yeah, so this is like C7 plus of the equilibrium gas phase, and that we will see later on that this is very closely. This actually very closely represents your little RS curve, which is the CGR. So you can also say the CGR. So the C7 plus or C6 plus or C5 plus, that represents in the well stream composition or the equilibrium gas composition, the CVD experiment, that very closely represents the little RS or the solution oil gas ratio of your produced well stream composition. And so that's why we have seen how the RS curves look like, and if you plot the C7 plus or C6 plus or C5 plus content, it has the same shape as the little RS. And then this is like, and the liquid dropout is just a mirror image of the C6 plus or C7 plus content, because then this is representing how much condensate we are losing in the reservoir, and this is representing how much condensate you are producing at surface.
There's that question.
Okay. Yeah, Eric.
Yeah, so you have a liquid dropout curve there, or it seems like. So I was wondering, how much liquid dropout do you need for this CVD experiments actually to be meaningful, or these measured properties? Maybe Hans Christian can comment on that as well.
Yeah, so
because the reason why I ask, because I'm working on a very lean gas condensate now. I mean, we're up to 50,000 cubes per cubes in GOR.
Yeah.
So yeah.
Yeah. So generally, like I think if you do the measurements in the PVT lab, generally you need very sophisticated PVT cells for accurate measurements of these small volumes that you drop out in the PVT cell. And we have seen PVT labs providing very bad quality liquid relative volume data just because they are using old cell, the mercury based cells, where you have to find this interface manually. But there are also for the same for the same fluid type, like where the maximum liquid dropout is generally like 2 to 3%. There are labs which can provide very accurate data because they are using more sophisticated cells. So I think it's more related to the type of PVT cell you are actually using. And also regarding the gas composition, so as I mentioned, that if you have very lean gas condensate, then it will be more difficult for you to accurately measure the composition of the equilibrium gas phase, because if you will lose very small amount of the liquid phase in the pipeline from which the gas is flowing when you flash it at surface, or the single stage flash in the PVT lab, there will be a lot more error in the surface CGR. So then, like for example, core lab, they generally use, for example, cryo for accurate measurement. Yes.
But you have good wellhead samples. I mean, 200 bars above the dew points, so I'm not worried about the quality of the sample. But
just a comment here. It's first of all, you see a lot of things when you're doing the CCE experiment, because you get a liquid curve from that too, to see how much you get. And one problem we have with the well we have now, it's because it's mud contaminated, and if you have mud contamination, a lot of the liquid dropout could probably be from the base oil and not actually from the reservoir fluid itself. So, but the problem is that if you have too low liquid dropout, it depends on the cell. You get problem to measure the liquid dropout into the cell, and you will not get sufficient samples to analyze at the end. You will don't get enough stock tank liquid at the last stage. Yeah. But to get a maximum limit there, it's difficult to say. But 2, 3, 4, 5% maybe, and if that's also contaminated, so you have to take to account contamination too.
Okay. Thanks.
Yeah, so generally, like if you have very lean gas condensates, and if so, what Hans is talking about is this. We go to the next slide. Yeah. So if you look at this compositional table here, so you have this the oil saturation, the relative moles removed. So that's your produced moles divided by the total moles, and then you have gas Z factor, gas gravity, gas viscosity, and then we have the compositions. And then the last stage, which is 500 psi, you have two composition. One is the equilibrium gas phase, and this is your equilibrium oil phase. And generally, like if you have very lean gas condensate, then this liquid oil saturation measurement, this will be more uncertain because you have very small volumes that can be accurately measured. And then sometimes you don't have enough volume to measure the final stage oil composition. And in that case, PVT lab, they just tell you, okay, we didn't get enough volume to measure the final oil composition. And this final oil composition is actually very important if you want to do the QC of the CVD experiment. And that's something we will look at tomorrow when we do the exercise. Yeah, I think. Yes, Hans?
Oh, no, okay. Yes, that's correct. And I will just say that if you first do the CCE experiment and you do the liquid dropout curve for that one, that will tell you a lot of what decision the lab will take and recommend you to do. So it's only based on that analysis. You can and you probably, when you have to do a CCE experiment, you can use a simulation program like PVT Sim just to simulate the CVD to see if there is any chance to do a good experiment. Because if you don't have a good experiment, you cannot use these results to do any tuning on it, and then it's meaningless to spend a lot of money on that kind of analysis.
Yeah, and it's a very, very, very valid comment, because you can use the CC experiment to design the CVD experiment and see if you can get enough volumes that can be measured accurately in the lab. And like, I think if you can do it in house, that will be great, and then you can make these decisions by yourself. But if you will let the service companies to decide it, I guess they will always recommend you to do the CVD experiment, because it will cost more money to you.
Not always. Some of the server companies are honest, and they said that this is not recommended.
No, actually, they are doing what Hans Christian just described. I mean, using Stratum, I can say that. So I mean,
okay.
So the Stratum said that you don't need a CVD experiment. We cannot do CVD experiment.
No, they didn't say that, but they are just performing the procedure that Hans Christian just described. I mean, simulating the using EOS to simulate how much liquid drop.
But again, like PVT labs doing this simulation with an equation of state model, that's also sometimes dangerous, because then what they like, if they have measurements and they see, okay, the equation of state model is predicting very different results, then they just try to they can just try to correct the results with an equation of state model to make it look more realistic. And then, like, if that's the end objective of the PVT data, that you try to tune an equation of state model, you will be more happy with the results, because then it will be falling very closely with your EOS models. Okay, so I think Hans, do you want to say something?
No, it's okay.
Yeah. So now we will just discuss like what is important in the CVD data, because we have a lot of information there. So why different quantities are important and for what purposes. So the Z factors, we know that these Z factors can actually give you the gas formation volume factor, and these Z factors are usually very well predicted, even if you haven't done any tuning of the EOS models, because these are just mainly related to the volume shifts of the lighter components. Most important PVT data, that's something we have like I have tried to emphasize before, that the most important data is in the CVD test is the compositions, and especially the N plus component in the CVD gas, which can be either C5 plus or C6 plus or C7 plus, because that is a very close function of your produced CGR. So this is something I was mentioning before, that if you plot, for example, the C6 plus content, it's very small here, but the C6 plus content in the CVD removed gas versus the solution GOR or OGR, this little RS or the RV from the CVD experiment, you will see that they have identical shape, and that's why this C6 plus or C5 plus constant is a very strong function of your little RS or the RV or the producing OGR. So so we can plot this C6 plus content as this value here versus the solution OGR, and you see it's a very, very strong function. So, and that's why, like, when we develop the equation of state models and do the EOS tuning, if we have good quality compositional data from the CVD experiment, then that is given more emphasis compared to the liquid dropout. And the main reason is that this, like, if I plot this little RS versus pressure, I know that all this area that's highlighted here, so that's from the initial reservoir pressure to the abutment pressure, all this area is actually the producible condensate that I will get at the end of my field life. and all this is the lost condensate that is gonna be in my that will be lost in the reservoir, and I would like my equation of state model to predict accurately this little RS curve, which is and the PVT data that we are measuring. That's this yn plus, which is a strong function of this little RS. So if my equation of state model is predicting accurately the CVD gas composition, and especially this C6 plus or C5 plus component in the CVD removed gases, then it means that it will give me a very good profile of the producing CGR for my well or for my reservoir, and then I should be more confident in the producing surface condensate in volumes and the recoveries of those of the condensate, of the surface condensate. And the real challenge is that most PVT packages, they don't let you see how good or bad your EOS is in predicting this compositional data. So that's another challenge. So, but like we in-house, we use the Spacecom software where you have all the flexibility in seeing the K values, the compositions, everything that that labs, PVT labs, they can measure. We can predict that with an equation of state model. Okay, so the quality checks, we have two types of material balance: the backward and the forward material balance. Backward material balance, something that we have already seen, like when we were discussing the separator test quality check, that we calculate the initial fluid composition and compare it with the lab value, and this is it gives a very good QC of the compositional data, because it's not much dependent on the relative oil volume, because it only takes the relative oil volume at the last stage. It only uses the oil saturation at the last stage. So if we have, even if we have this lean gas condensate fluid system, and if we have very high uncertainty in the liquid saturation measurement, but if the gas compositions are measured accurately, then this material balance should be very good. Like the backward material balance should give us very good results, and it should indicate whether the compositional data is measured accurately or not, because it removes this oil liquid final the oil saturation measurements out of the equation. And then in the forward material balance QC, it's an overall material balance QC for the CVD experiment, and then we have this is very well explained in the CVD with an or paper. So that's something that we will upload that paper in the reference folder, in the papers folder that we have on the directory. And here we calculate the equilibrium oil composition at each pressure stage, and using the initial fluid composition and the oil saturation at each stage. So, and then here we have equations. I guess yeah, we are getting close to the time, so I think I will just go through these equations when we will be doing the exercise. So it will be a good refresher of the CVD material balance just before we do the exercise. Very good. So yeah, so yesterday we started discussing about the quality checks of the CVD experiment, and any CVD experiment which has some kind of removal, we can do a material balance check. So we had a material balance check for example, for the DLE experiment, and now we are discussing the CVD experiment, and here we also have material balance, and we can do two types of material balance here. we can do two types of material balance. One is the backward material balance, and it's very similar to what we saw in the DLE. So it's so this is similar to DLE material balance for the composition. And here what we do is we calculate the initial fluid composition from the information that we have, the measured data we have in the CVD, and most importantly, the liquid saturation data that we have in the CVD experiment. We only use the final stage oil saturation. So this material balance actually gives us a very good QC of the CVD compositional data, which we went through, that it's very important to be measured accurately, and because that gives us the information of the well stream composition that we will be producing with depletion in the reservoir. And most importantly, the CN plus, or like C5 plus, C6 plus, or 7 plus of those compositions is directly related with the solution OGR that we are going to produce, and that tells us how much barrels of condensate we will produce at surface, which drives the economical value of the gas condensate reservoirs. So and like, for example, if you have a lean gas condensate reservoir, we were discussing this, that the oil saturations can have large uncertainties because of the small volumes being dropped out in the cell. So in those cases, if the compositions are measured very accurately, the backward material balance should be very accurate for such fluid systems. Forward material balance, so that's discussed in very detail in this with Centaur paper. And Matthias, I think you have already uploaded that, right? Yeah. So that's also in the recommended papers that in the directory. Okay. And what's the difference between the forward material balance and the backward material balance? Is that in the forward material balance, we calculate the equilibrium oil composition, that's your XI, at each pressure stage, and we start from the initial fluid composition. That's why it's called forward. So we start from the initial fluid composition and go towards the abundant pressure, and then we calculate the equilibrium oil composition at each pressure stage. And knowing this and all these information from the CVD test. And here we are using the oil saturation of each stage. So that's why it's an overall QC of the CVD experiment. And generally, if you have rich gas condensate or near critical fluids, where you have more and more certainty in the or more confidence in the liquid saturation measurement, then this forward material balance should be reasonable for those fluid systems. Yeah, so now we will just discuss the backward material balance first, and that's the most important material balance because it gives us the good QC of the compositional data. And backward material balance, what we are doing, we're calculating the initial fluid composition by knowing all this information. So we have the removed gas composition. So this is YI is the removed gas composition at each pressure stage. We also get the moles removed from the CVD experiment. So these are just the incremental moles of gas removed from the PVT cell at each pressure stage. So K represents here the pressure stage, and then this sum product here actually represents how many moles of gas we have removed from the PVT cell at all pressure stages until the abundant condition. And then at abundant pressure, since we have two phases in the PVT cell, one is the oil phase and the other is gas phase. So at that condition, the residual, so this represents the moles of component I in the oil phase, and this represents the moles of component I in the gas phase at the residual pressure or the abundant pressure. If we sum all these moles, then we get the total moles that should have been present in the PVT cell at the dew point or the initial pressure. So this is the total moles of component I, and this whole numerator, and then in the denominator we have sum of moles of gas produced plus the oil moles and the gas moles at this abundant pressure. That's our PN, the last pressure in the DLE experiment. So again, so this gives us the total moles present initially in the PVT cell, and then this Ni over NT represents the mole fraction of component I in the PVT cell at the initial pressure state. So we are calculating this Zi, and then since we have the lab reported Zi, we just compare those numbers and see how big the difference is. So how it is done? So here we have if you look at the CVD experiment, you will find out that you have this Yi reported. We have this gas moles reported also in the PVT experiment. So how do we calculate, for example, the oil moles and the gas moles at the abundant pressure? Those are not reported directly in the CVD experiment. So those we have to calculate. Xi is reported at the abundant pressure, and we also have the Yi reported at the abundant pressure. So the main thing is how we calculate the oil moles and the gas moles at the abundant pressure. That's also here, NOR and NGR. So that's being shown here. How do we calculate these two values, NOR and NGR? So we know that the volume at the saturation pressure, the initial volume in the PVT cell, it's simply you can calculate from this PV equals to NGRT. So we know the gas Z factor of the dew point gas. We know the total moles that we assume generally that we start with the 100 moles, and we have the dew point pressure and also the temperature. So we can calculate what should be the volume of the PVT cell at the saturation pressure. And now there are different ways of getting this NOR and NGR, so the oil volume at the residual pressure, at the abundant pressure, and the gas moles at the abundant pressure, the residual gas moles and the residual oil moles. So the first method is that if you know what is the residual oil density and the residual oil molecular weight, then we can simply use, for example, this relationship here for calculating the moles of the residual oil, and that's simply the density times volume. So that's your mass of the mass of the oil divided by the molecular weight, and the volume of the residual oil is simply the relative oil volume or the liquid saturation at the last stage. So that's what we talked about before, that it uses the liquid saturation at the last stage, this material balance. And we have the saturation, the volume at the saturation pressure, and we know that in the CVD experiment we always keep the volume constant, same as the volume at the initial conditions. So that's why we can multiply this liquid saturation, which is the volume of the oil divided by the total volume of the cell, and total volume of the cell is the same as the volume at the saturation pressure. You get the oil volume at the residual conditions, yeah, so here, so that's how you can calculate the residual oil moles. And the residual gas moles can be calculated in two ways. One, you can calculate, you know the total moles initially, that's 100 moles. And then we can calculate the sum of moles of gas produced from the PVT cell. And then we can calculate, we have calculated this moles of the residual oil. So if we have total moles of the gas removed and the moles moles of oil present in finally, then we get the moles of the residual gas present at the abundant pressure in the PVT cell. And the other way to calculate is simply to use the ideal the real gas law, PV equals to NZRT. We know the gas Z factor for the gas at abundant pressure. And the residual gas volume is simply the volume, the total volume of the PVT cell, which is equal to the saturation pressure volume minus the volume of oil at the residual conditions, which we have calculated before. So that's one way of doing it. And the other way is that if you don't know, if the lab hasn't reported the residual oil density and the molecular weight, then this NGR, the moles of gas at the residual condition, is the same as this number here. And the moles of the residual oil, then we can calculate that with knowing the moles of the total moles in the PVT cell initially, the moles of gas removed, and the moles of gas at the residual conditions. So we will do an exercise on this on the CVD backward material balance and try to apply these equations. And I think that it will be more clear with the exercise. Forward material balance. Again, you can go through the paper. It is very well written and very detailed. And there are other things in the paper discussed, like how you can generate black oil tables, for example, for gas condensate reservoirs with the CVD experiment. But in general, in forward material balance, what we are trying to achieve is to get the mole fraction of each component in the liquid phase. So that's Xi, the equilibrium oil phase composition at each pressure stage pK, and that's simply you have the so this is the moles of the this NT is the total moles at any given pressure stage. So NT, so there are the forward material balance takes it has more computation compared to the backward material balance. So you have to calculate the total moles remaining in the PVT cell at each pressure stage. You have to calculate the total composition that's changing in the PVT cell at each pressure stage. So you have to calculate what's the total composition at each pressure stage. The moles of gas at each pressure stage. The composition is usually it's always reported in the CVD experiment, and then in the denominator is the same information. So here are the equations that you can use to calculate all these parameters. So we need this, and we need this to get the equilibrium oil composition. And we will see why we are calculating the equilibrium oil composition and how it can be used to QC the CVD experiment. So NGK, that's the moles of gas at each pressure stage. That's simply, you should know the pressure and the gas factor and the volume of the gas. And volume of the gas is simply the total volume of the PVT cell minus the relative oil volume at the given pressure stage times the volume at the saturation pressure, which is always the total volume in the CVD experiment. And here you can see that we are using the liquid saturation at each pressure stage in doing the material balance, which was not the case in the backward material balance, where we only use the last stage relative oil volume. The total moles in the PVT cell at any given pressure stage is again we know the total moles initially minus the moles of gas we have produced. So that will give us how many moles are remaining at any given pressure stage in the PVT cell. And the total composition. So again, we wrote it like this, right? So we need to know the moles of component I at pressure stage K divided by the total moles at pressure stage K. So NIK, that's the total moles of component I. That's simply how many moles were present initially. That's 100. Usually we take 100. That's your NS. We represented it as NS before. Minus how many moles we have removed from the PVT cell in form of as an equilibrium gas. Yeah, and NTK we have already calculated before. And then once we have all these three parameters in this equation, we can calculate this equilibrium oil composition at each pressure state, and then compare the equilibrium oil composition at the final stage with the lab reported XI. So we know that in the CVD experiment, PVT labs, they measure the residual oil composition. So yeah, so once we have calculated the XI at each pressure stage, we can compare the last stage calculated XI with the lab reported XI. So that's one QC. The other is that you can actually calculate K values, and you can calculate the K values knowing the lab reported YI, because that's measured in the lab, and the calculated XI. And we know that this ratio is the K values, and you can calculate K values at each pressure stage and then plot it against pressure for consistency. That's something we will discuss on last day. What is like what do we mean by no crossing of the K values, and why it's a consistency check? And yeah, and one just one information that I can share here, and that's something Curtis also mentioned yesterday, that when we are tuning the equation of state model, the best data that you can have for tuning the EOS model are the K values, because that's really driving everything in the equation of state model calculation. And from the PVT labs, we generally get PVT data that is indicating how the K values are behaving. Like, for example, we get the liquid saturation, we get the saturation pressure measurements, but we don't get directly the K value data from the PVT labs. It's very seldom that you get that kind of data. So if you have a very good CVD experiment, and if you find that all the measurements are done very accurately, and the forward material balance and backward material balance, they are closing very accurately, then you can actually use this K value data in the tuning of your equation of state model, this calculated K value data. And we have used it sometimes, like when we have to do very complex equation of state model tuning with a lot of binary interaction parameters that we will go through again in the not the next topic, but the next to next topic. And sometimes we have to go through very complex EOS model tuning, and there we need some kind of K value data to control the regression. Yeah. So yeah, so that's just a comment on this. So here on this slide, we will just briefly talk about what is the importance of the material balance, the CVD material balance, and mainly here we are only talking about the backward material balance, because that's really giving us the information on how good the quality is for the compositional data reported by the lab for the CVD experiment. So if we have, for example, if we have a gas condensate reservoir with an initial OGR of, for example, 250 STB per mmSCF, and the lab reported, for example, the lab reported CN plus, so this could be your C6 plus, for example. So the lab reported C6 plus content or C7 plus content in the total composition, or your well stream composition, is, let's say, 10%. And when we calculated from the material balance, we got, for example, 8 mole%, which is, and we know that this C6 plus content in the composition is directly related to your solution OGR that we saw yesterday. So it means that it is in the calculation is indicating that the solution OGR is about 200 STB per mmSCF. So now, if the CVD removed gas compositions are measured very accurately, then it is indicating that, or if for example this lab reported initial fluid composition is measured very accurately, it means that we have lost some producible condensate volume by 20% in the lab while doing the CVD experiment, because this is representing that you have lost some of the C6 plus content in your removed gas volume. when we were removing this high pressure gases from the CVD experiment, and we will see how the compositions are measured. But when we were removing it, so some of the condensate was dropped in, for example, pipelines, and it was lost, and the C6 plus content in your removed gas volumes was measured less compared to the lab data. So it means that the 20% of your producible condensate, because this C6 plus this translates into your OGR, which is giving you how much condensate you can produce. So you have lost about 20% of the producible condensate volume.
Just a comment, Bilal. This is also reflecting the initial condensate in place number.
Yeah.
It's the same number. So let's say that our reservoir is containing 1 trillion standard cubic feet of gas, sales gas. That would mean that you've got 250 million stock tank barrels initially in place.
Yeah.
Of which you might be recovering 30%, which obviously is a lot of oil, a lot of condensate. And instead of having that 250 million stock tank barrels of initial condensate in place, the lab, through these procedural errors, has lost 50 million stock tank barrels in the laboratory experiment. So that 10 mole percent, no good engineer has a relationship to. Okay, and the 8 mole percent, is that a lot? Well, it's 20%. Okay, well, 20%. But you have to realize that C6 plus mole percent is directly proportional with the stock tank barrels initially in place and initially being produced for every gas unit being produced. So these are big numbers. So the 20% is an unacceptable material balance error by the laboratory, and you wouldn't want to force the equation of state to match the 8 mole percent or the C6 plus being produced over the CVD experiment, because it's basically got too little condensate that it's producing. So I think it's just it's also initial in place as well as the initial revenue, which is probably even more important, of course.
Very good, Curtis. And on the other hand, if we look at the forward material balance, then we know that the errors, like in the forward, if you have material balance errors, then that material balance error could be due to the uncertainties in your liquid saturation measurements or the CVD removed gas composition measurement. And generally, if you have lean gas condensate, we discussed this yesterday, that these liquid saturations can have more uncertainty because of the small volumes, and this forward material balance may look very bad for such fluid systems. So yeah. Okay, so now we have just 2 more slides on the PVT experiments, and we will just go through briefly some important comments about the experiments, and then we can take any questions on this topic. So like when we started these discussions on the PVT experiment, we like these experiments, they were designed like CCE, CVD, DLE. These experiments were designed way back in the I don't know the history, when people started doing these experiments. But like for example, when the DLE experiment was designed, it was mainly designed to get the black oil PVT properties for the oil samples, which required correction with the separator test. But the main idea was to get the oil properties that can be used directly, for example, for any engineering calculations, because at that time equation of state models were not being used extensively for PVT, for getting PVT data. But nowadays, the objective of all these lab data and PVT reports is generally to tune an equation of state model and then use the EOS model to generate black hole PVT or other use, for example, for your simulation models or pipe flow calculations, etc. And yeah, lab data is very seldom used as is in engineering calculations, especially these experiments like CCE, CVD, DLE that we went through. This is another point that we discussed briefly, I think, previously, and we will talk more about it, that the robustness of your tune equation of state model increases as you have as the range of your data, the lab data that you are using in the tuning of the EOS model increases in the pressure, temperature, and the composition space. So if you have larger pressure, temperature, and composition space for tuning your EOS model, the EOS model will be more robust. And that's something we discussed when we were discussing the reservoir representative samples and in situ samples. That's the whole idea behind using any reservoir representative sample in tuning your EOS model. That because any reservoir representative sample is coming from your reservoir fluid, it is originated from your reservoir fluid, and that composition and any PVT data on those samples should and always be used in the tuning of the EOS model. And that gives you a very robust equation of state model that can predict PVT data for any composition that you input in the model. So now we have different experiments, CCE, CVD, and DLE. So what is the difference if we think about those experiments with this perspective, the pressure, temperature, and composition space? So we know that the CCE experiment has a constant composition. You put one composition, you don't remove anything. So you have one constant composition that you are flashing at different pressure stages. So you are measuring data that corresponds to the K values as a function of varying pressure only. You have a constant temperature, you have varying pressure, and we are not changing the composition, the total composition in the PVT cell. And remember, when we discussed these K values, let me just, how do you? So remember, when we were discussing these K values, so that's your K value of 1, and that's log of Ki versus log of pressure. And we were discussing that these K values, they generally, it's a very bad figure actually, but all the K values, they tend to converge at one pressure. That's your convergence pressure. And the K values at these high pressure, so if I just separate these high pressure, these is, for example, your high pressure. So at these high pressure, we know that the K values are dependent. So here the K values are a function of your pressure, temperature, and the convergence pressure. And we also discussed that this convergence pressure is the function of composition and temperature. So if you have a different composition at any given pressure, we are changing these K values dramatically. So in the CCE experiment, we have a constant composition and a constant temperature. So you have a constant convergence pressure, but these K values, they are changing with respect to pressure only. Okay, but if we look at, for example, the DLE experiment, that's completely on the other extreme, where where we are removing the equilibrium gas phase, and we have a very drastic change in the total composition, at least in the first pressure, in the first depletion stage. And so in that case, we are changing the composition. So we are also changing this convergence pressure, and also the K values at high pressures, they are changing not just because of the pressure, but also because of the change in the total composition, because the convergence pressure is moving. And similarly, the CVD experiment is somewhere between the CCE and DLE experiment, where you also get the compositional effect on the high pressure K values, but the change in the total composition is not that extreme as we have in the DLE experiment. So when we are deciding, for example, which experiments we should be doing, so we should have these things in our mind, that the CCE experiment gives us has a constant composition. DLE gives us the dependency of K values, not just on the pressure, but also the compositions, the total composition, and same goes with the CVD experiment. And on the other hand, the multi-stage separator test, that corresponds to the K values at low pressures generally and temperature, and there the K values, we know that they are not much dependent on the total composition. So what types of PVT experiment should be performed on each sample? Like when you have this the objective that the data will be used for equation of state model tuning, then the types of PVT experiment that are generally done depends on what type of fluid you have. Also, how much is the variation in the composition among the different samples. So if you have 10 samples from the field, whether they have very similar composition or they have varying compositions, how many samples you have, sample volumes, and also, of course, the budget that you can use for doing the PVT experiments. And so let's have, for example,
I think there might have been a question. I'm not sure if they were.
Yeah. Okay. I didn't see the hand.
Yeah. No. Just Bilal. You mentioned the composition. They are different. That's just a function of the number of steps, right? That you have. There's nothing else intrinsically different with the way we are extracting the fluid.
Yes.
Yeah.
Is that correct?
Can you repeat, Gerardo? There was a break in the sound.
Yeah, Alexandra, I think you have your microphone on. Okay, I'm gonna mute her. Yeah. So Bilal, no, you mentioned the changes in composition between the DLE and the CVD and the difference, but that's just a function of the number of steps we have, right?
Number of.
Well, I think it's a function of the number of steps, but also the process itself, because the DLE removes all of the gas, right?
Yeah. Okay.
So that has probably the most profound effect. The CVD removes some of the gas, which has less effect, and the CCE doesn't remove any gas. So it's, constant composition. So it's to some degree a function of the number of steps, but it's probably more important whether the DLE has the biggest impact on total composition.
Okay.
But what he's saying is that it doesn't usually have a big effect on the K values. The only exception to that really being near critical oil, DLE. A near critical oil DLE, in the first step, you may remove half of the solution gas so the composition going from being a critical composition with K values converging to 1 to being something that's far removed from critical.
Okay.
Just slightly below it. So that's probably the only exception to the rule.
Okay. Thanks.
Yeah. So just for as an example, for example, since we are working a lot on common equation of state model development for these unconventional basins. And we have Eagle Ford, for example, Montney, Permian, Scoop and Stack. And there we generally see that generally you have a lot of PVT reports, and each well, like your producing well stream composition can vary from like very lean gas condensate or even wet gas or dry gas to very low shrinkage oils. So if you have such a wide range of compositions, if you have samples with such a wide range of compositions, then even if you just do CCE experiment on each of those experiments, and if the CCE experiment is done very accurately on each of those well stream composition, you would already have this very wide range of pressure, temperature, and composition space. The K value data or this or like the data that corresponds to the K values for this very wide range of pressure, temperature, and composition space for tuning your equation of state model. In that case, even if you don't do any other experiments like CVD or DLE, but if you just do CCE experiments on all of your samples with very wide range of composition, that should be very reasonable for tuning your equation of state model. Okay, so I think this was the end of the topic, the lab PVT experiment, and we have an exercise. Yes, Gulnar, yeah.
Yes. In terms of all experiments that we have,
it's very hard to hear, Gulnar. Can you speak a little bit up?
Do you hear me now?
Yeah, now it's very good.
In terms of all PVT experiments now, what you're saying is basically we can go with the CCE experiments and then tune our model, basically. Is that what?
Yeah, what I'm trying to convey here is that for equation of state model development, we need, like, if you want to have a very robust equation of state model, we need PVT data measurements on wide range of composition, pressure, and temperature space. And if you have samples that are like that range from that already have a very wide range of composition. So let's say if you have, for example, compositional gradient going from like the top structure is very lean gas condensate, and then the bottom structure, bottom of the structure is very low GOR oil. And if you have collected samples at each depth, for example, you already have samples with very wide range of composition. And if you just do, for example, CCE experiment on all of those samples, that should be good enough for your equation of state model. But on the other hand, let's say if you have only one sample collected from the field and you have only one composition, in that case, you would try to do, for example, CCE and DLE or CVD and a multi-stage separator test to cover that, to some extent this wide range of composition space to tune your equation of state model.
All right. Okay. Thanks.
Yeah.
I think put another way, in an ideal world, you could tune the equation of state more reliably and with less ambiguity or more certainty with a different set or type of experiments than we normally collect in the industry. That being said, the most important data that would be required to be from an alternative set of experiments would be the compositional data. And the compositional data is the most difficult for what the lab to measure accurately, consistently. So there's this, like, it's true what Bilal is saying, but it's difficult to get good quality compositional data. So some of these other experiments, like the CCE liquid dropout curve, is a very reliable, should be a very reliable set of data that reflects indirectly the K values, the dew point, the bubble point, the liquid volume changing. It's an indirect reflection of the K values, but it's a very reliable set of data. So if you could combine some of that type of data with some data that has reliable compositions, that would be the ideal world in a sense. So, but you have to make use of what's there. Yeah, that was a comment.
Yeah. Yeah. I don't know if maybe Gulnar might have misunderstood me. So, yeah, what I was trying to say is that if you have, like, if you collect different samples at in the field, and those samples, the total composition that you have measured for those samples, that vary a lot from one sample to another. Let's say one sample is like a lean gas condensate, the other is like is a black oil, and you have a very large number of samples going from lean gas condensate to the black oil. And if you just do a CCE experiment with, as Curtis is saying, that you have only measuring, for example, liquid dropout or the oil shrinkage, the liquid saturations. For those compositions, you already have the data that is reflecting that is an indirect measure of the K values with varying composition, pressure, and temperature. And you can use that data to tune your equation of state model without having these other experiments, CVD or DLE. But on the other hand, if you have only one sample, you have one composition, the total composition of the sample, then you would try to get more PVT experiments to get these to get the data that reflects the K values with varying composition, pressure, and temperature. Yeah, okay, I guess so. There is an exercise on this topic, and I think we will do, or maybe we can do the exercise now and take the break. I think that's a good idea, I guess. So if we go to the exercise portal. Okay, so this is an exercise on the backward CVD material balance, and all the data that you see in the red, this is taken from the PVT report we have. So we have the pressures for the CVD experiment, the gas Z factor, the gas gravities, and then we have this liquid saturation, and you can see that's about the maximum liquid saturation is 38, straight going from 0 to 30, about 38%, which is indicating how near critical this gas condensate is. And then we have the gas compositions measured at each pressure stage until here, and then this is the residual oil composition. And then we have this NP over NS, which is how many moles of gas removed divided by the total moles initially in place. So that's this. And then we just need to do the calculations here. So we need to calculate what was the volume. So the final goal is to calculate this initial composition and compare it with the initial composition reported by the PVT lab here. And to do that, we already saw that there are certain things that we need to calculate first. So first we will calculate what is the volume of the PVT cell initially, and for that what we saw in the slide, that we can use this real gas law, PV equals to NZRT. So we have the moles actually. That's the total moles that we are starting at. We are assuming that there were 100 moles initially in the PVT cell. So that's the moles. And then we have the gas Z factor of the initial gas. That's this one here. And then we have the R. That's for our field unit system. And then we have the temperature, 250. And that should be in Rankine, so adding 460 here. And then divided by the pressure, the initial pressure, which was the dew point pressure, 6726. Okay, so that's the volume initially, and then we have we need to calculate the volume of oil that is present in the PVT cell at the abutment pressure, which is at 500 psi. So for that, we know that the total volume of the PVT cell should always be this number here, and then we just multiply it with the oil saturation at 500 psi. That should be this. Because this is VRO is in percentage, so we just have to divide it by 100, and that's 31 cubic feet. So out of 138 cubic feet, there is 31 cubic feet of the oil at the 500 psi, and then the volume of the gas phase at the 500 psi will simply be the total volume minus the oil volume at residual pressure. The gas volume, we know the gas moles present at 500 psi A. Now we can simply use this PV equals to NZRT, for example. So we know the pressure. So where is 500 psi multiplied by the volume, and then we just divide it by Z and R and T. So we have the R here. Again, the T should be in Rankine, and then we have this gas Z factor for this gas. Here. Yeah, so 7.38 moles, and then the moles of the oil phase that's remaining. So that should be so that should be how many moles we have initially. So how many moles we have initial minus how many moles we have produced as a gas phase. So that is sum of these numbers here. This delta NP, the incremental moles, that's calculated already here. And then minus the moles of the gas phase. Okay. Yeah, and now we just need to use the equation that we have shown here. So it's very messy. Just delete this, and then you can take the snapshot. Why doesn't work? I will just take. This computer is hanging forever. Okay, let's do this. Yeah, so we have the sum product of the gas compositions and the incremental of moles of gas produced, so that we can sum product of the gas compositions. So if we are talking about the for H2S component, and then we have incremental moles here. And these should be fixed. And then we have plus the moles of the residual oil times the composition of the residual oil plus this needs to be fixed. And then moles of the residual gas times the composition of the residual gas, the gas at 500 psi, and then divided by the total moles. So that is the sum of all the moles produced. That's this. I hate this computer. Plus the residual oil moles plus the residual gas moles. This has to be fixed. This also has to be on this one.
There's a question from Eirik.
Yeah.
Good morning. So can you just explain that NS assumption, that 100 mole?
Yeah.
I didn't catch that.
Yeah, so we just need to, to do the material balance, we just have to assume like what's initially in the PVT cell, and then that's just the basis of our material balance. So like 100 moles, if we say that 100 moles and that is in the PVT cell initially, then we can say, okay, because in the CVD experiment, they generally report NP or NS, which is the percentage of the moles recovered, and the percentage of the moles are on the basis of the initial moles. So the basis for these moles that are produced is the initial moles. So if we say that there are 100 moles initially, then we can just simply take this data as the number of moles produced in the CVD experiment.
Thanks.
Yeah. So we can, this 100 moles, we can also start the material balance, let's saying 1,000 moles or 500 moles. 100 is just is a good number to keep things clean. But like if you can say 1,000 moles, and you will see that the material balance will remain the same. All the results will remain the same. The final material balance calculation. Okay, so where is the B24 and K24? Yeah, so that's this. So that has to be fixed here, and then this has to be fixed. Let's see, fingers crossed. Yeah. Okay, so we just have drag the formula, and then now these are the calculated values from the material balance, and these are the lab reported values, and you see they are exactly the same. And you can wonder why. It's because if you look at the PVT reports, these you see that the names we have mentioned here, that these are synthetic PVT lab reports. So these reports are not the actual lab PVT reports. These are created with some kind of model. So that's why there is a perfect material balance on the data. But yeah, but if you look at real data, you will see some deviation. And if you don't see any deviation, then you should start suspecting the lab, I guess.
Just a comment. What are you thinking about? You said you definitely will have a kind of deviation between the back calculation and the lab. What you should normally that you accept as limits for different components? Do you have a thumb of rule or something like that you normally use?
Yeah. So generally, backward, like if we talk about backward material balance, generally we accept 0.5 to 1 mole% difference, for example, in methane, because methane is generally the component with the largest amount. So either methane or like C7 plus is, we know that's the C7 plus or C6 plus is usually the very important component, because that translates into your CGR, and there we should not have difference more than 0.5 mole%. But of course, it also it may differ from one fluid to another. Like if you have very rich gas condensate and if you have 0.5 mole% different, versus if you have very lean gas condensate and if you have 0.55 mole% difference, then the percentage error would be larger in the lean gas condensate, for example. But generally, yeah, we 0.5 mole% is very common to see mole% difference. So meaning that the difference between the lab minus the calculated value, that should be.
Another question from Hans Christian.
Yeah, Hans. Yeah.
No more question. I just was thinking of one thing, but it was not relevant at all.
Okay.
Okay.
Very good questions. Just one thing that like earlier when we've done this exercise right here, for those of you who haven't maybe been exposed to that many CVD experiments before, there's a question we've got many times: is why in the pressure column there, why is it two pressures at the 500 and different compositions for that?
Yeah.
And I think it's important just to if you can just mention the difference between the two there.
Yeah. Yeah. So you see that here when we are doing the material balance, we have this R represents the residual pressure, or like the residual oil or the residual gas, and that's at the abundant pressure, which is 500 psi, which is the last pressure in the CVD experiment. We have two phases. We have an equilibrium gas phase and an equilibrium oil phase. So this composition here, that's why we have two pressure stages, like two pressure columns with the same pressure, 500 psi. So this pressure here is the composition here is the equilibrium gas composition, and 500 with the star, the composition here represents the composition of the equilibrium oil that should be measured by the lab, because that is used for doing the material balance QC. So that's the composition of the residual oil or the equilibrium oil at 500 psi, and you don't get these measurement of the equilibrium oil composition at other pressure stages. It's only done at the last stage. Maybe we should have, yeah. If you look at I think it's in the PVT report. This is so if we go into the PVT report and try to find the CVD experiment. Yeah. So here you see that 500 with the star, and then you have this comment here that that's the residual oil composition. Okay.
Good.
Curtis, any comments from your side on the lab PVT experiment? We finished that topic now.
Yeah, not really specific to the details. I mean, I think the thing to carry away is that there's certainly lab uncertainty in both so-called PVT data and compositions.
Yeah.
That has to be accepted and dealt with. And for the gas condensates, the CVD removed gas compositions are really very, very important to getting right and to modeling correctly. So there, all this compositional material balance checking is to ensure that what we are tuning and matching with the equation of state are proper data, particularly the amount of heavies, the barrels per million numbers. And so it's just, I think a lot of people, they pay a lot of money for the lab reports. They see a lot of numbers with a lot of significant digits that are often certainly not justified. They struggle to get those numbers into the PVT software, and then it's difficult to know kind of, what levels of accuracy should be expected and what levels of prediction accuracy should be expected. And so it's lab data doesn't come from above. It comes from a laboratory with normal people with normal problems and normal laboratory equipment error, problems. So we just have to recognize that. And that's why having more data than less data is helpful. Just like any experiment, the more data points you have to define a trend of any measurement, the better. Of course, the quality of the measurements are more important than the number of the measurements, but some combination of the two, and trying to identify which of the data you have are more accurate, less accurate, and accordingly to weigh those data up and down. So I think these are some of the important takeaways from the PVT experiments as we see it.
One question, Curtis, on that. You mentioned briefly that maybe some of the default go-to laboratory experiments today are maybe more of tradition purposes than potentially maximizing the value for the at least the tuning of the equation of state. Would there be like a couple of key missing points or data points that you would like to see in kind of like a dream case scenario for data more frequently from the labs?
I think at the top of the list would be oil relative volumes, meaning that you measure both gas and oil volumes in every CCE test conducted, even lower GOR oils. because that what I call relative oil volume, or basically the relative amount of oil and relative amount of gas below the saturation pressure, is such a strong tie to the K values and to the phase equilibria, that getting that data is really important. Now, we usually get it, we often get it, we'll get it for gas condensates, but often not for oils. So that's one thing I would argue strongly for. And I think a lot of the labs actually have the data, but they don't report it necessarily. So that would be the top of the list. And I think the second, because of this uncertainty in the compositional measurements of removed phases, of removed gas phase in the CVD and the DLE, there's and the problem comes from there being such a small sample taken out often and getting the composition of that right, and the laboratory, there's a lot of reasons for the uncertainty there. But you want sometimes very accurate PVT data for a range of compositions. So another way to get that data is that you just do 2 or 3 or 4 recombinations of separator samples, for example, and CCEs of those mixtures. So I would take any day of the week 4 recombinations of separator samples with the CCE of each over a DLE any day of the week. Probably even the CVD test. Because there, the uncertainty in compositions is very small. You know, you basically have the separator gas composition, the separator oil composition, and it's this recombination ratio that's really the only uncertainty, and there's limited amount of error coming there in the lab. So there you can get 4, quite wide-ranging compositions with very minimal uncertainty in the compositional data, and 4 pieces of really good data, CCE with this relative oil volume for each. That kind of data would be second on my list, because I know we're never going to go there. It's hard to sell that to the industry. Well, I needed DLE data. Okay, well, I don't want to even go to the arguments there, but those 2 pieces of data I think are probably the top of the list. And on compositional data, it's the measurement of the flashed oil density and molecular weight always being provided. If they want to make calculations and adjust those and say we believe in these calculated numbers better, that's fine, but they should at least give us the measured density and molecular weight of the flashed oil in all cases. So I think those are the top 3, if I'm going to make a list.
Yeah, very good. So I think this is a very good point to take a short break, and then we'll return with the next being, or we have a question, Gerardo, we'll do that first.
Yeah, just one question. In when we have a gas condensate field with, let's say, 50, 100 meters of gas column, and you take different samples at different depths, how important is it to get the accurate temperature in those tests when you do the CVD? And what I'm after is, how much does it have an effect, the fact that we are wrong on temperature, and that's very seldom the case, compared to the different components that we have along the vertical on a gas condensate?
Yeah.
Yeah, I mean, if you ask me, I would say it's not very important getting the temperature right. You're not going to be very far off. And then once you tune your equation of state to, let's say, 3 CVDs from 3 gas condensates through the column, and you find out that all 3 temperatures are somewhat off, they should, you decide later, well, it doesn't really matter because you're tuning the equation of state to the 3 sets of data at almost the right temperature. So as soon as you get that equation of state, you can just finish tuning. You can just change the temperature for that sample at the bottom to a different temperature and predict the CVD, all the PVT properties at the, let's call it the right temperature. And likewise in the middle and at the top. So I myself would say it's not a critical issue. I mean, as long as you're not talking about 100 degrees, or even 10, I wouldn't worry about it. It's like a second order effect, maybe a third order. Yeah.
Okay, thanks.
I
Yeah,
don't know.
and just for the audience, because I normally find that we do exploration wells, we get our samples, but the temperatures we're wildly guessing. And then on an appraisal well, we might test, and then we get accurate temperatures.
No.
And this is what I was after. Yeah.
Yeah, the equation of state within the range of temperature uncertainty you're talking about here, a properly tuned equation of state shouldn't have any problem in predicting at adjusted temperatures. No.
Okay, thanks.
Bilal, do you agree?
Yeah, 100% agree. Actually, we are just doing one study for one of the clients, and so that study is involves actually the equation of state model development, fluid initialization study, and usually the temperatures, the in situ temperatures, accurate measurements of those are usually important for your fluid initialization. And they have done all these tests without knowing what are the exact temperatures at each depth. They have already collected samples, and we have tuned the EOS model, and now we are moving forward for the fluid initialization, and everything is looking very good there. So it's generally not a major concern with respect to the EOS model tuning.